if we're running out of, any amperage we run on these little micros, this is enough as far as wire gauge.
Yeah.
Well,
Yeah, I was looking at those exactly that size. I didn't get as far as seeing what the current spec was.
Okay, let's let the fun begin, shall we?
Hmm.
It's good to see everybody here today on Wednesday, December 13th, 2023. Welcome to the Propeller Live Forum. And I'm showing you my slides plus the slides on the side. It's a little bit messy, but I was just having trouble with Google Slides here. So this busy picture shows what we're talking about today. It's really three things. We're going to wrap up a hardware redesign that we're doing at Parallax, which is the Flip module carrier. So I want to talk briefly about that. And if you're just jumping in watching this video, there's a prior video on our YouTube channel from the Propeller Forum in November, where we discussed this, and this is how we arrived to where we are today. There have been about 300 messages and emails exchanged between then and now, and a lot of work done by Michael. So we'll talk about the Flip carrier, and then Lachlan, if he's here. Yep, he's here from Australia. Good morning.
Morning.
And thanks for getting out of bed so early, and you can talk about your 64-pin Cockroach series.
Mm-hmm.
And then whatever's left, Chip will talk about things he's doing with the compiler to make it easier to use, and the analog to digital improvements. Sound good?
Sounds good.
Right. And if anybody has any kind of anything important to you, if you just message me via the chat, I can get the right person's attention on it anytime. So, or if there's something you just want to share at intermission, if we had such a thing, we can do that too. All right. So without further ado, we want to get to Michael pretty quick here. So I'm going to run you through just a little bit of history of where we've been and why we're talking about this important Propeller 1 project today. Way back about 10 years ago, we created this board called the Propeller Project Board USB, and we made them in Asia. And now we make everything in Lachlan. So this is an older design. We no longer build anything in Asia. Everything's built in Lachlan. And this board we used to build in 1,000-unit quantities, and it had kind of a high cost. It has a propeller circuit built into it. So that combined with the power supply and it just not moving very well forced us to obsolete it. And this also came out before we had the Flip module in mind, which is a much better Propeller 1 solution that we want to lead people to. And I think a lot of you know from building products, you really want to optimize your efforts around a few good things. And we don't want to be setting up our manufacturer machines to make similar but different propeller circuits all the time. It's just ridiculous, But if we make one thing that really moves well, like the Flip module, then we want to put our efforts around that. So that's what we're doing. We're simplifying, also enabling us to simplify, but making a better solution for our customers. So back in July, we did this thing where I put this board out there on sale and I made it really cheap. And then all the customers came out of the woodwork who were using it. And they said, whoa, we love this board. Where are you going with this? We use this in our classrooms. Like one of them is Mike Harrison, who's here. He uses all kinds of our products. And we discussed how we would like to end this product and make something better for our customers at the last forum. So that's kind of where we are today. So we got our main users present through the sale and end of life announcement. They all came forward, and two of them that I'd like to draw attention to today are Mike Harrison with Great Bay Community College. He's here. And also Kenichi Kato, who is from Singapore Institute of Technology. And these are a couple of big users. Like Kenichi uses several hundred of whatever we make each semester. They run a massive, pretty big mechatronics robotics program through on Parallax hardware. So we didn't want to leave him stranded. So I grabbed the rest of our hardware from inventory of the Propeller project boards, and I kept them for him to use next semester. So anyway, if you're out there, Kenichi, those are in my office. I got them for you. We'll get them over to you. We just haven't arranged that yet. Okay, so that being said, we asked these customers, Kenichi and Mike, what are you guys doing with our stuff exactly? You know, what are your needs? And they produced these pictures back with globs of wiring and all kinds of things attached. Student soldering projects with relays and 12 volts and different sensors that are familiar and usually wired up to bigger things. Breadboards attached. This is from Kenichi. And then this is that's an omnidirectional set of wheels on a robot. You know, you can see a camera. You see the HCO4, the knockoff of the world-renowned ping ultrasonic sensor from which all standards are set. And I don't know what that is in back. But anyway, there's a propeller here. So lots of things. So these two guys, Kenichi and Mike, gave us all their input, and then we produced a requirements document, and we came up with what Michael's going to share. But first, let's look at what Mike Harrison also shared with us. He sent us a nice presentation showing some applications of theirs and then talking about how the flip could be used. So here you see a display, some push buttons, a joystick was added to this. So kind of like more common microcontroller type stuff, sometimes leveraging, you know, the true hardware features of the propeller or software features for video and for keyboards and things like that. But we see a lot of more common microcontroller applications that just make use of the multi-core. And they're often using Blockly Prop as a programming language. So here's his famous tic-tac-toe game. Oh no, this is the stoplight. Or is it Simon? Simon, yeah. So you have lots of things and they're all on my desk.
And notice the Radio Shack in the background.
Yeah. And by the way, as I go through your pictures, feel free to say anything, okay?
Yep.
Thank you. So yeah, talked about mounting pads, the importance of them, washers, and the propeller activity board was thrown in there for some of its special characteristics. We like double or pre-tinned and double-sided boards with header rows. You know, the ability to connect to other things that we commonly use at Parallax that our customers use was brought up. And then this would be the tic-tac-toe game.
Yeah, tic-tac-toe.
Okay, and he's using a flip on a proto board, so that's good that you're already using the flip and you found a way to make it work conveniently. Yep. Power. So the power requirements from these educational customers of ours are all over the place. They're 3 volts, 5 volts, and 12 volts with relays. So the flip provides some of those power options, but not all of them. And we talked a little bit about P1 activity board, what we call the propeller activity board, WX. And how we want to match it. And then Mike pointed out here, I envision a 10-pack packing to be a small brick of boards with no accessory, keeping costs down. So our goal with this effort is to allow our educational customers to have a low-cost project board where they can solder and learn to solder something really cheap. And I'm talking $10. No manufacturing at Parallax, no profit at Parallax, but allowing them to take their flips from project to project. So reducing the project cost of using the propeller.
And the, you know, the board you have up on the screen now, the activity board, the circuit overlay, the little tiny one, I use that from time to time. But way back days, you had the blank 3x4.
Yeah.
And that, you know, definitely fit the need, and we could put that as a daughter card right on top of the activity board. Activity board stays in inventory, and these go with the student.
That too. And I could bring that board back, and that could also be used with the Flip carrier board or Flip Protoboard that we're talking about now.
Yep.
For more expansion area. So That's pretty clear then, what we discussed about the cost goal for the model for the customer. Everyone's got that? Low cost project boards, and then being able to move the flip from board to board. And so, before Michael takes off here, I just want to thank you, Mike, Harrison, and Kenichi for giving us a lot of input. And Michael carefully considered it with me, and we bounced a lot of things back and forth to arrive at what Michael's going to show you today, which has gone through 3 iterations in the last 24 hours. And our goal really is to get this done, because if you do the math, and you're all engineers, but when you put your business cap on, if you do the math, you could pretty much figure out that Parallax probably makes about $15 on a flip module, because you could reverse our bill of materials, and we'll make nothing on this. So in these designs, we like to be able to recover what we're doing, and we'll have to move 500 to 1,000 boards, or I think 500 to 1,000 more flips to justify the expense of creating the Flip Protoboard. So our educational customers will be seeing a lot of this, and we'll be calling on them to consume to help keep this effort viable. End of sales pitch. Michael. Thanks, Michael, for staying up late.
No problem. Right, let's share this screen up there. This one. And so hopefully that's screen sharing now. Is that coming through?
Yep.
Awesome. Okay, so as we were just saying, thanks to Mike, Harrison, and Kenichi for their input, and this is a good chance to get some feedback along the way. So there's a few kind of experimental things on here just to see what people think. And I guess if I just quickly go through and explain the sort of 6 or 7 things that there are, and then see what you think. So standard parallax board size. The flip module would plug in the middle, as you can see in the socket there. It's set out so that the idea would be you plug the flip module in the front, or solder it directly in if you wanted to, always. But the bottom of the board is also labeled, so you could build your project on the bottom if you wanted to have a completely uncluttered build space. So that's the idea there. The reason for having it in the middle is that it gives us the closest way to break out all the IOs. We've got another version of this where we've tried having it at the top and on the side. The trouble is you just end up with traces everywhere breaking out the IOs. It's not very efficient, and you kind of lose space as well in doing that. And so I just wanted to show you this and see if you could get your heads around it and see if this seems to be a way forward. It gives you the space on both sides, which is bigger than the standard mini breadboard. From the photos I saw from the educators that gave us photos, they're not using more than this space. Typically, they use sort of half of this space, with the exception of Mike's games, which fill the whole board. But I'm thinking, again, if you built your projects on the back, then you would have the space, I think, to put your array of buttons and lights on there for your tic-tac-toe game and whatnot. Anyway, I can send you the files in more detail with dimensions and stuff later, so you could actually verify that. But that's the working theory. So feature-wise, where do we start? Let's just start from the top, I guess. So I stuck a couple of LEDs on there, labeled L1 and L2, and they can be controlled here between the middle of the flip, you've got pads hooking L1, L2. So you could just drop a resistor from each of those, either down to an IO pin or to the LDO voltage rail if you wanted, or to the 3-volt rail, or even the 5-volt output rail if you wanted to see the voltage, you know, from a power supply, or if you wanted to control it with an IO. So it just gives you flexibility there. Then there's the row of big screw terminals. I've made a note, Mike, about considering the smaller ones, the 2.54 pitch. It's really just a question of making sure that those screw terminals are going to be good for all customers, I think, who might want to use this. I'm just thinking in a sort of, you know, those small 2.54 millimeter terminal blocks usually are only good for 1 mil squared, cables. They're quite small. Maybe they're just a bit too small. Maybe I need to look at the options out there to see if, you know, what's the biggest one we can get in terms of cable size, but they do seem a bit small.
Michael.
Yeah.
It's John McPhailin. You may consider 3.5 millimeter. I've been using those on some of my custom P2 expansion boards, which also fit on a board I made for the Flip. So, or not expansion board, eval board. At any rate, you know what I'm talking about. But there is a 3.5 millimeter terminal size that is kind of nice in between those two. It's useful. You know, you're not going to get giant wires in it, but you might find that helpful. Yeah,
good call. Good call. I've written that down. Thanks, John. So
And
the terminal blocks are there.
Oh, sorry. Using Cat 5 or Cat 6 cable.
Yeah, that would go in no problem.
Yeah,
that would go in no problem. Yeah. So these terminal blocks are currently labeled T1 through T6, and they're brought out on the ProtoBoard on the edge here, as you can see, the left-hand side. So again, the idea being that you could put your, you know, whatever components in here, resistor, NPN, transistor, MOSFET, whatever you want to use. And you've got the 2 voltage rails just above, 3.3, and the LDO voltage rail, and the ground rail there. And of course, the IOs just to the right. So I've yet to build one and try it, which will be the next step. But I'm hoping that kind of brings everything in a nice local area that you could build quite efficient circuits there. So that's that. And then next to that is an on-off array. Haven't quite thought that through yet, but just put it there for now. We did something similar on the P2, on the latest P2 breakout board, which enables you to either fit a switch or fit a shunt, or even just don't fit anything and just use it for voltage out, or, you know, whatever. But just, I saw on your photos you had soldered switches to the side of the board, which I could imagine the mechanical stress of that and probably the cost of the switches can be quite something. And I just thought, well, maybe in the classroom, if you could have a sort of standard switch or a bunch of switches with a short flying lead with a connector that would plug onto here, you know, the students could use that as a remote on off. And then maybe if they take it home later, you could keep your switches and just give them a small shunt to go over the header pins to create an on off. Or I don't know, maybe the switches aren't that expensive. But anyway, it just seems like it gives a way to allow you to have switches without that mechanical stress on the side of the board. So, and also provide somewhere that you could hook a scope ground on if you wanted, or you know, remote switching anyway. Next to there's the barrel jack. Now the PCB is laid out to accept either a barrel jack or another screw terminal. If you fit a screw terminal, let me flip this round. If you fit a screw terminal, I've hidden 2 holes under the barrel jack. So obviously you wouldn't have the barrel jack there. And you'd probably have the screw terminal perhaps on the other side of the PCB. I've just shown it here so you can see what's sort of going on. The thought was that if you were to use something like, oh, of course, the camera's not working, is it? Anyway, if you were to use a battery box with a couple of flying cables coming off it, you might be able to stick that to the bottom of the PCB, feed the cables through these little holes, and then straight into the terminal block. So it could be quite a neat little sort of battery-powered portable solution. It's just a thought. So that gives you two ways of getting power into the system. I also was thinking about the XT60 connector that Kenichi was using. And actually, again, he had it soldered hanging off the edge of the PCB, which of course you could do. But again, that seemed like quite a lot of mechanical stress there. With that whacking great connector, it'd take a bit of force to plug those things in and out. So I was thinking for that solution as well, it might be better to get pigtail XT60 connectors and just screw them into the terminal block connector. Anyway, it seems like this is a fairly versatile thing, and I'd be interested if you still felt you'd rather have big pads here that you could solder onto, then there's no reason why we couldn't put those back there. It just seemed like that might be a tidy way of doing it.
The power design right up the middle there, that power all looks good. And where you have it both sides also is excellent.
Yeah, and it's right where we need it. I'll come back to the backside in a minute. Obviously, you've seen a sneak peek of the LDO. Oh no, let's do the LDO now, because that's related. So next to that is the LDO footprint. So that's as you had before on the previous project board or proto board. So it's just a footprint, and I've put space for a couple of large ceramic caps either side on the bottom, right where the heat is. So not the best position at the moment, but anyway, and a couple of through hole parts on the top for decoupling. And then the 5-volt output from there goes to these LDO rails. So if you don't fit that regulator, you can use those for whatever you like.
While we're looking at rails on the bottom, you had some 3.3 also on the bottom edge of the board.
Yeah, the LDO is repeated in a couple of places,
Oh, okay.
3 places there, and also
Excellent.
3.3. I'll mention that in a minute, the rails at the bottom in relation to microbus compatibility. Mustn't forget that. So that's your LDO option. And then above the two capacitors on the front, we have the JST sockets for quick I2C. I was thinking it'd be nice to add one I2C socket onto the system I2C bus. And then I was wondering, should we have two to allow customers to have I2C on a different pair of pins? Johnny Mac might have an opinion on that. And we kind of had the space there. We kind of had the space there. So I thought, well, let's give that a try and see what people think of that idea. And then so the system connector is hardwired into P8, P28, P29, the Propeller I2C bus pins. The aux one is connected with, at the moment, Y and Z, because I couldn't think of anything better at the moment, into clock and data, and they're on the proto board there. So you could just jump that over to P24, P25 if you wanted to, or any other pin, obviously. So that's what's going on there. To the right of those, there's a set of 4 accessory headers. So you could use them as, BRW standard parallax type or servo type accessories if you wanted to, or you could use them as 4-way accessory headers. Not entirely sure about that yet, but it's kind of a work in progress and coming along. But anyway, it's a place to break out some IOs. The voltages are white discs at the minute. I was thinking, although those white discs are too small, but I was thinking ultimately it might be nice if someone could write the voltage in there, and then maybe we have down the right-hand side here, V1, V2, V3, V4, and then people could jump onto 3.3 volt or LDO if there was a row of LDOs there, voltage rails or something like that. So haven't quite kind of got my head around that yet, what to do with voltages. We could just fix 2 of them at 3.3 and maybe 2 of them at LDO. Anyway, there's some breakout there. It'd be interesting to see if people think it's worth having that sort of header format there, or they'd rather see just the 3-pin and not bother breaking out so many, or whatever. So that's that. Reset button, I thought, well, it's quite common to have a reset button footprint, and the reset button on the Flip would be maybe quite difficult to press with if the barrel jack's installed. Maybe it's quite good to have a reset button. Could be repurposed, of course. SIP. So here's the Wi-Fi SIP footprint. Again, you could use it for anything else, but if you wanted to plug a Wi-Fi SIP module in there, you could, and then program and debug and control stuff over Wi-Fi. So take the chance to put that in there. A through H, they're just the connections up to those servo headers for the IOs. And they're positioned such that a 1/4 watt resistor would fit in that gap nicely. If you wanted to have a series resistor to protect your IO pin on the Flip. And then on the other side, you could run a pull-up resistor or pull-down resistor if you wanted. So that's that. Yeah, and then the rails, lastly, I think the rails at the bottom are just configured such that a micro bus click module would fit straddling the LDO for the 5-volt rail input on a module and 3.3 volt for the 3-point side. And you could put one micro click in there. You could put one on the back side of the PCB over on the right-hand side. So there's a couple of options there to use that standard. Oh, and yeah, okay, come back to that as the very last thing. So on the back side, yeah, just try to duplicate labeling. These white squares are just so you could just mark them with a color Sharpie if you wanted, or write something on there, just a user identification. There's a white square on the right at the moment if a student wants to put their name on it or something. I don't think there's anything else on the back that I've missed. So I'll just quickly go back around to the front. And then this extra set of holes in the middle, I just put them there to see what people think. Would you rather have, get rid of those and just have, more more through holes? Or is it useful in your projects to have somewhere else you can mount holes? At the moment, I've just set that middle one such that the distance between the short distance is 1 inch and the longer distance is 1 3/4 inch. So some of the parallax brackets, like the ping bracket and the, what's the other one? Speaker bracket, I think, they're on a 1 3/4 inch pitch. So you could just put a couple of ping sensors directly on there if you wanted. Or whatever universal hardware. So that's sort of a question whether having that extra mounting hole is of any use, or really it should be gone and we should be filling it with more or other things. I think that's pretty much it. Yeah, I think that's all. So what do you think? Any questions?
Yeah, I have a question. Maybe it's obvious, but it's not obvious to me. I am assuming that on the flip module connectors, down the center, each pin on that, each pin there is connected to the hole next to it. Is that correct?
Correct. Yeah.
Okay.
Yeah.
Okay, so that's where you can. How about the other pins, like to the right of that or to the left of that? Any connections there?
Actually, what I've done so far is I've connected. I probably can't see a little white tick there, or sorry, a little white dash. But so the pins to the right of the socket are connected,
right,
to the relevant thing. The pins on the inside, actually, I did kind of go back and forward with that a little bit. And at the moment, they're not connected. I was thinking that maybe that gives more flexibility if the middle ones aren't connected, because you could possibly put a 3-pin package in there. Maybe not many people are going to use the middle pins. And maybe if people are building on the other side of the board, it might be a nuisance to have all of those middle pins taken up. So I was kind of, I haven't quite got my head around the inside yet, whether you think they should be connected or not. These L1 and L2 are the only features that encroach on the inside, and they could be moved up. We could put just another row of holes at the top there above, you know, out of that area. So we could connect the first inside pin to the neighboring IO if you felt that was a good idea.
But then you just have one middle row of free pins inside.
Yeah, which seemed a bit of a waste to me.
I agree.
Especially as it's quite easy to, if you're going to fit a component with a through hole leg, you can easily bend it over to join onto the IO.
Yeah, if you're going to be soldering on the board anyway, that's what I do.
Yeah.
They want to get off the box.
And then I think it's quite flexible. It's quite handy to have 3 pins there.
It would be synergistic with.
But a question, Michael, to consider, you have one outside column available where you're showing the little white hash.
Yeah. Which is a bit small, but yeah.
No, that's fine. But if you did 2, then it would allow some of us, me, to solder in a second set of rails like you're showing there, those gray rails, so that I could use male pin headers to attach things to pins.
Yeah, that's a good reason for doing that.
You know, I've noticed that I got a board from Malaysia for another processor, and they did that, and I didn't understand it at first, and then it made perfect sense, especially when I was looking at signals, you know, the logic analyzer, which I think in the education, you know, world, I think it's Mike is doing a lot of that, you know, showing youngsters how to use a low-cost logic analyzer would probably be a big benefit to their process, and that would facilitate that. The second thing I was going to ask, and again, I recognize my own biases here, because I've standardized on the P2 accessory board format for a whole bunch of stuff. I've got 10 boards I've already built, and I'm ordering another 6 next week. And I made a board that is a shrunk down version of the eval board that I can plug a flip into. So I have 4 of the 2x6 headers on there, so I can use the same boards. You know, in most cases they're compatible, but you know, at Elite Laser Tag, we're still doing P1 development too on active products. So this works really nicely. On that, then, would you consider, or, you know, am I the only one that thinks it might be nice to have a 2x6 P2 accessory header, maybe adjacent to the ABC, that ABCDEFG, that block, you know, over there in the lower right-hand corner, so that you could attach, you know, a P2 accessory header board that might be compatible with the P1?
I think if it's going to be used, then it's a good thing. I think, you know, because of the pitch, you could also just solder a header in.
Yep, you're good.
But I hear what you're saying. It makes it one step quicker and easier for you just to have it pre-wired. I mean, the other place it could go, if we ditch these middle mounting holes, is top left, alongside the T1 to T6, assuming the LED doesn't get in the way of the width of the accessory header. And then P0 through P7 could be used. Mind you, that would then take them away from T1, T6. Anyway, yeah, I mean, for sure, we could. I'll write that down.
It's just, you know, there was, you in particular, I think, spent some effort developing that P2 accessory format, and now I've absolutely grabbed onto it. And because, you know, at the laser tag company, I'm the only electronics guy, and oftentimes people don't understand how much time it takes to build a board. So I you know, with the company's blessing, I've taken every kind of sub-circuit that we use, and then anything I could think of that might be practical, and I put it on a P2 accessory board type format. And now I can plug that into my P1 dev board, you know, that my P1 eval, or a P2 eval, or a Johnny Mac, or one of the other boards, and I can knock together something that's working pretty quickly.
Yeah, we'll definitely revisit that. And the reason that actually we didn't put it on there already was really because you could just fit a header.
Yeah, yep,
But as
you're
I
right.
say, I do accept that it could be handy if
Yep.
it was just silk screened for that. The same reason, I'm glad you brought that up, because it was the same reason that we didn't put the VGA footprint back on there. And maybe we should just be careful that people don't need that. But it takes up so much board space.
Right.
And,
Yep.
and nowadays you can buy a really low cost VGA breakout from, anywhere, Amazon and the like, and then just run your cables in and add your resistors if you need VGA. So I think the days of needing that custom slim and somewhat expensive VGA socket probably are gone. So that was sort of the logic there as well, why we left that off. Thinking of things that would be easy for people to fit to the proto board if they needed it, and not sort of trying to encumber everyone with all those extra features. But the P2 accessory header is a contentious one. There are accessories that would work even in the parallax range. So,
Yeah, and you had marked that A through H, so that would be a good spot. Well, any of the 4 groups other than the last 8 bits, because that gets a little bit difficult. But the other thing that you invoked my name during the I2C header commentary. It's actually, I think it's a good idea what you're doing. It's nice to have it on the EEPROM bus and also separated, because the P1, when it boots up, it has an odd I2C speed. It's about 200 kilohertz. And I have connected things to the I2C bus on the P1 that have caused loading the program from EEPROM to fail. There are some I2C devices that are too slow, and they garbled the bus. So that's a good thing. What I've also been doing is putting a 5-volt I2C bus on my boards, because there's a lot of things like there's a lot of sensors and displays and things like that are 5-volt I2C, but that requires to do that is 2 FETs and 4 resistors.
Yeah. I just actually wonder from that, maybe we should we just ditch the system quick connector and just have the one socket there, just wired to whichever pair of pins anyone chooses, because you could then wire them to 2829 if you chose, or to 2425 or anything else really. Maybe from what you're saying, maybe having the so-called system I2C sockets not really worth it.
I'm not saying that. I think what you've done is quite nice. If you had more room, I'd say throw on a 5-volt version that is connected to the aux. That's what I did on I have a laser tag gaming piece that I just did for the P2, and I have a quick connector on there, and then I have a PH, the JST PH, that's 2.5 millimeter, but that's a 5-volt version, so I can put displays into that, and I can put quick into that. But again, the 5-volt thing has a different VCC, and then the SCL and SDA lines are buffered and brought up to 5 volts.
Okay. Well, I'll look into that, and maybe there's something to be done there.
Okay.
And the other thing just to mention is that I've put the sockets on sort of backwards, arguably backwards. That was so that it's easier for people to hand solder these pins after the event. Just to mention that in case anyone says, "Oh no, don't do that. That's going to cause problems." Because once the capacitors are on, it'd be jolly difficult to solder those pins if they're facing inwards.
And want to remind everybody too that all these parts would be in a bag, so the customer would assemble this board.
Yeah.
And do you think you would offer just the bare board?
We could. I want to minimize the decision-making part for the customer as much as possible. Are you thinking to save a few dollars, Mike?
I'm more thinking to use this as a daughter card on other applications. So if we had projects moving to the P2, or even when we use this as a daughter card on the activity board, there's no reason to waste all those parts.
Yeah. Yeah, we'll talk about that, maybe with you too, a little more, but the expectation is this pile of parts is no more than a couple dollars cost.
Right.
Yeah, and sometimes like even, wasting parts in that way is a benefit to us, not stocking things multiple ways. But
Yep.
You're thinking like you're inside the building, which is good.
And
Does anyone
if
have any opinion on having those two LEDs on that board? Is that just a waste of time, given that you could just solder LEDs anywhere on the proto board anyway?
They're good.
They're good to have, are they?
I think so. LEDs are super cheap, and it's one of those things we almost get them for free as long as we can have our ring or kidder person throw them in a bag quickly. It's no big deal.
Well, that's the thing. And again, what color do you bag and stuff? People might have their own. Because there is one thing that the Flip module does have two LEDs on it already. So if you needed a kind of onboard indicator, you've already got one.
Right.
So yeah, that's a question mark whether we get rid of those LEDs or leave the footprints there.
And
Or
the
whether they-
LEDs on the Flip, they actually do shine through a board like this. So
Yeah.
if you're mounted upside down, it does shine through.
So Mike, would this make you happy at Great Bay Community College?
Yes, it would. And the only piece I see right now is down at the bottom where those 3.3 paired headers are. If you just give me a jumper, rather than dedicate all of those to 3.3, because 3.3 is all over the board. Give me a jumper so when I'm needing to build other power, a 9 or a 12, on a TO220 package, the jumper makes that row viable to bring my power down to that row and disconnect it from 3.3.
Good.
Yeah, makes
Excellent.
sense.
If we don't do it as a simple slide on header, then I'll probably take a X-Acto knife and cut the land. And
Well, they're currently in 4s, I think. So perhaps if I just cut them in half, so you've got 2 lots of 4. The middle
Yeah.
one would be unconnected, and then you'd have 3.3 connected
Yep.
to the or the other way around.
right, I can add a header between the center where you put the brake.
Yeah, or just a blob of solder.
Yes, exactly.
Okay, let's split those in half then.
All right. Well, anything else, you could just contact us, let us know, put it in the chat. We'll harvest the chat log, and expect to see prototypes, which may or may not look like what we're looking at today, pretty soon.
But do double check where the 4 corners exist and where the screw holes are, because I do plan to use standoffs off of my activity boards and other boards. And you've been pretty good about the same footprint all along.
Yeah, it's actually written right there. Verify mounting holes, XY position, sizes, plating, and ground, and verify the screw terminal clearances as well, because sometimes those screw terminal blocks are, some of them will stack together and some of them won't. You need a slight clearance. So yeah, I'm ahead of you on that one.
Yep,
But
good.
yeah,
Thank you.
for sure. What did you, Mike? Did you have any preference about having this extra mounting hole for your classes? Is that a waste of time or a handy thing?
I think for all the ways we've been using it, it is a waste of time. Where is it? I got a piece right here on my desk. There it is. When I need to hang a monitor or something off, I use your existing screw hole and some strap aluminum.
Yeah.
And I can mount anything off the top of that board.
Yeah. Yeah, so we'll. I think we might just get rid of those and use that space for something else yet to be determined.
Yeah,
maybe a P2 accessory breakout on the left-hand side or on the right-hand side. Yeah. Okay. Some good feedback there from everyone. Thanks for that.
Yeah. Thanks for everybody, and Michael, thanks to you.
I had one quick question about possibly having a surface mount area on there.
For what sort of components?
For like an SOI C8 or just a variety of some of the smaller chips that are surface mount. I know that some of the Parallax boards had, I think, two footprints on some of theirs that came in handy. It's not a big deal. but I
Yeah,
don't know if there's any room. I wouldn't want to lose any of the regular through hole pins though, because those are a premium. But there's times that if there was an area that wasn't being used by any of that, that you could put a small SOIC package or something like that on there, would be nice.
yeah, we'll definitely revisit that once we get the proto layout sort of locked in and see where if we can squeeze something in sensibly. We definitely looked at it, and it's certainly something that was on the existing project board. Again, we sort of took them off for a similar reason to the VGA, and it's just that it's so easy to buy little SOC or SOIC or SOC23 breakout, nowadays, and on a 0.1 inch pitch, and then just plug that into the proto board. So it was just from our research, we didn't see much evidence of people actually using those.
Okay.
But yeah, definitely, especially if some space opens up somewhere that we need to need in inverted commas to fill with something, then yeah, good point. I've jotted it down.
Thanks, Jim. Good to see you too.
Yep. Hi.
Okay, then. Michael, we can tuck you into bed right now. Well, somebody will, hopefully. And we'll move towards Australia.
Sounds good.
Thanks a million.
Yeah, looks good, Mike. I
Absolutely,
really
Lachlan.
like that. It's it looks useful.
Now,
Cheers,
here's a
Lachlan.
face we haven't seen in a while. Welcome back.
Yeah. Good afternoon or evening, everyone. I've been working on a breakout board, or sorry, a concept, I guess, using a 64-pin IC socket, which I found is still available thanks to the 68,000 series of CPUs, and also some of the Yamaha music chips. The SIC socket and its format seems to have a nickname of the Texas Cockroach, which some of the 68,000 series chip designers christened it. And what it is, it's what they call a shrink dip format. I'm just going to share a screen here and show you what it looks like. So has that come through okay?
Yes,
Yeah.
looks good.
So this format, when they were trying to package up the 68,000, unless you shrink the pitch of the pins, you end up with something which just seems pretty monstrous. They described it as looking like a Hershey bar because it ends up being over 3 inches long. You've got 3.2 inches on each side. So they came up with this shrink dip format, which is close to 2.2 inches long instead of the 3 inches. And that means it's not that much longer. It's about 13% longer than a P1 dip IC. And the other thing which is good from a P2 point of view is that the width between the two rows is 0.75 inch or 750 mils. And as you know, the P2 has got a fairly large package, and what it means is that the P2 can fit inside of those two lines of two rows with a little bit of wrangling, like a very minor amount of filing. So I'll just skip to, hopefully I can skip to a comparison. This is an adapter board we made up which adapts the what we're calling the TC64, the Texas Cockroach 64 format to a P1 dip IC. And that gives you an idea. So it's just that little bit, about 13% longer and about 20% wider. The full width of this board is 0.85 of an inch, or 850 mils. Okay, or about 21.5 millimeters for the metric people. 64 pins is close to ideal. It lets us bring out all the I/O, except for the SPI pins. And we made a decision that we'd just have to do the SD card via an accessory header, or via the accessory header is the answer. So if you look at the format of the pins, we've got the prop plug in the bottom left corner of that screen, and then you've got P0 up to 27 along the bottom, and then you swap over to the other side, and you've got 28 up to 57, and that means that, sorry, I'll come back to that. And then you've got the 3 volt power. Effectively, it's power out to because the boards we're using have a regulator on board, and you've got the 5 volt input for bringing power in. So the advantage of this is that you can put like a RAM breakout on these pins 40 up to 57 on that side, which we'll come to in a moment. So I should speak just briefly about the need, or why we think we need one of these standards, and there's probably 2 drivers for it. One is that a lot of the other platforms have a stackable system, so for instance, Arduino, Raspberry Pi, have common shields or hats, and we don't really have something similar that goes up in the vertical direction for the P2. And part of the reason for that has been, the width or the suitability of some kind of system which doesn't sort of blow out and become quite large quite quickly. And the second reason is to look at a board which can also be soldered to a baseboard in an OEM style thing, such as like the Raspberry Pi Pico does. It's got the castellated headers, and so you can just solder it down to a baseboard. And when you do that, you need to have something that's reasonably compact. And this can be adapted, just by castellating the pins, which we'll get to in a moment. So are there any questions up to that point, just talking about the header and the breakout and the format? Okay. All right, so these are some prototype breakouts and accessories that we've made to fit this format, and we'll run through these. But in that bottom left corner, you'll see the castellated sort of solderable format. So what I'm saying, I guess, is that we could take that P2 board here and just cut off those things and run a castellated version, which we could then solder down to a main board. And we've put some extra ground pads on that, which would allow heat to be transferred through, in addition to what comes through just by having the boards right up against each other. The other motivation for working with this is to use, there's a screen we like from 4D Systems, which has some good intelligence on it, and it happens to be around the right size to fit inside this cavity.
Oh, so and you can just plug that on top.
Yeah, that's exactly right. So you can stack that, put it on top. We can put some buttons or even hopefully some Gertzel touch pads down the left and right hand side to be able to scroll the display or interact with it. Or we can break it out to, like DVI or HDMI style headers. You'll notice also that the socket drops down a little bit in thickness at those ends, which sort of lends itself well to having an accessory header, which sort of kind of locks into that cavity. Yeah, so 4D, this is their board, which they manufacture, and it's pretty much the ideal size. We just have to shave, we just have to sand a little bit of those corner pads down without, doing any damage. So you can see that they just sort of widen out right at the end there. And you'll notice also that they've also got those castellated solderable connections, so it can be soldered down to an OEM style board. This is our first attempt at a breakout. So because you've got the 2 accessory headers on the actual module itself, so they're, P56 up to 63 on the left, and there's 24 up to 31 on the right. You don't need those on the lower breakout board. You've got the ability to connect accessory headers there. Obviously, we missed with the reset button, which needs to kind of squeeze in there, and we need to move some pads to make that happen. But this is always intended as just a mechanical prototype. On that P2 board, the basic board, you can see that we've just got space for 2 regulators and the flash and the crystal. So we're just keeping it, you know, bare bones. And I'll talk a little bit later about, well, we can talk now. We're also working on switching regulator boards or adapters which fit into that same footprint. So, you know, we'll have switching regulator options because there's some really nice parts from TI rated at 2.5 amps, which we like, and they accept up to 36 volts in. And so the idea is that we could use very cheap LDOs if you've got a sort of lower power application, or we can fit a switching regulator onto that if you want to run higher voltage or more efficient. Yeah. We had a go at seeing if we could match up with the Pi Zero footprint, and so the board at the top, you know, has the Pi Zero header on there, and we're going to attempt a variation of this where we actually cut off the RAM pins from the P2 basic board to lift it up a little bit, and that will allow these micro USB and hopefully the mini HDMI socket to actually fit. So if you imagine just having 1 or 2 pins in each corner here and the rest of them cut off and elevated, we're hoping that we can actually have something which actually fits in the standard case for the Raspberry Pi Zero. We've been working on some accessory, you know, various breakouts. This is one for prototyping. We've been toying with the idea of doing a version which actually would have a through-hole solderable HDMI socket instead of the pins on the right-hand side. This is you know, 4 accessory headers with a little bit of space around them, which would allow the 4 to be plugged in again on top of the module. And this is a cheap dual wipe socket, which do exist. I haven't been able to source one locally, but there are still these sockets available. We found a few suppliers. They range from about 40 cents each. And so your main board could have these dual wipe ones, and then you just use the machine pins for what plugs into them and what goes up the stack. Unfortunately, these aren't really stackable. You know, they have a high plastic ridge, and so it prevents them from really being useful in a stackable kind of configuration. They just don't have enough pin length to do that. And then I was just going to come back to, so because we've got the P1 breakout where it sits underneath, the socket, and so that can go down to any board which has already got a P1 design, and allow the P2 to sit in there. And so, you know, what we're talking about earlier with Michael's board, it would be possible to actually put this on top of that proto board that Michael's working on, and you could plug a P2 in, and on top of that you can actually put the next level where you could actually put this board which has got the accessory headers to break that out. And so there's a lot of flexibility with this, and part of the reason for that is, you know, some of our boards have a this is quite a large board which we manufacture. There's a P1 footprint in here, and you know, this is the shortcut to upgrading our boards to use a P2. And one other board I didn't mention, but this is a RAM board here on the left. So that's compatible with the you know, pin 40 up to 57 that the P2 Edge uses. And that's about it. So we're just, you know, we're working and developing on this at the moment to see how far we can push it. And
good question. With regards to the, if you have a RAM adapter, how fast is the P2 running on that board?
Yeah,
question.
We're waiting on, we've got these switching adapters which are coming, so they'll fit in where the regulators are. And we've also put on the next version of this board, there are some solder nut cavities under here which enable us to really get the heat out from the regulators and also from the P2. And so we think we're optimistic we'll be able to run obviously, Ada, your software is the benchmark for what we really want to be able to run. We'll see if we can do that. Yeah.
Yeah, it's kind of inexplicably become the benchmark.
Yeah, so we'll try. All we can do is provide mechanisms to get the heat out and spread it out. This board, this one at the bottom is actually like a heatsink board, so it's just copper planes and stitching, which is relying on the ground pins, to bring out the heat as best we can on that. The next version, we realize, if we put a cavity for a solder nut, then we can always put the solder nut on there, and then we can screw it to a proper heat spreader. And that that's probably as close to what we can get. The other thing is to just make a accessory board, which is got some tabs in it to mount a fan on there, so you could actually cool it that way, and that would be super efficient. We'll just probably use maybe a 30mm fan or thereabouts. Yeah, so that's about it. Any questions?
Hey, I'm just noting that you were able to find like a monolithic 64-pin socket that just made that whole thing go together, huh?
Yeah, we kind of stumbled across these by accident, and then there was a kind of a follow-up. Okay, well, are these things really available? And
yeah, there's probably like some old stock.
Sorry, Chip?
Oh, it seems like something that there'd be some old stock piled up somewhere, but it's hard to imagine they're still manufacturing those things.
No, they do still manufacture, and you can thank some of the industries adopted those 68,000 CPUs, and they're still using them, and so they're still making products which these things sit in. And so we found there's at least 4 manufacturers, maybe 5 manufacturers of these sockets. So companies like Pressidip or Milmax or Econ or Harwin, these companies kind of specialize in the turned pin, Swiss pin, or gas tight kind of sockets that you're familiar with. They're not hideously expensive, in quantities of one, they're under $5. You can buy them from Mouser or DigiKey. And then the dual wipe ones are a little bit harder to find, but we found those from overseas manufacturers around the 40-cent mark, so it's, we'd love it to be a slightly cheaper thing to do, but it's not prohibitive. The other point is that, the stack height on this is only, when you nest these sockets together, it's only 5.2mm high. And so you can have a P2 and then a RAM board and then a display. So these 3 things are on the left-hand side, and you're only at 15mm high above the board. Okay, and that's something else we like, because when you stack, if you did the same thing with Arduino, you'd be up, at 45mm, or, if you use standard headers. So by using the machine pins, you end up with something super compact. And we see that as an advantage, in a world where everything's kind of has to be shrunk and cute, to be able to compete. So, we were just mucking around with this, and then I was talking to Roger and Brian a little bit about it, and we think it's got legs, to make a stupid pun, but it's something we've sort of made up a few things, and we think, okay, well, this seems like useful, and we, in our application, we're always width constrained, and so we need things which are less than around an inch wide, and so everything, a lot of the things we do need to be around that kind of size.
That's a neat idea. I like it.
Yeah, thanks, Chip. Yeah, it's we're just we'll keep developing and pushing on it. We threw away a few things just to bring it back and keep it simple. But it's very solder friendly. So these pins end up being on a 70% of 2.54 or 0.1 of an inch 70mm pitch, or 1.8mm. So they're quite friendly to solder into a board, or to make the socket, the adapters up. It's a good kind of compromise between keeping something compact, getting something stackable, and also having the chance of building sort of more of an OEM style module, which could be soldered down onto a larger board. You know, but to integrate the switches. So yeah, we're just waiting on the next batch. There's some more breakout boards and the regulators as well, which and then we'll do some, you know, proper heat testing and just see how warm this thing gets. But we think we've got, you know, ways of mitigating all the things we can foresee at the moment. So yeah.
Hey, Lachlan, for those unfamiliar with your industry, maybe you want to tell people generally what you do.
Yeah, so we manufacture industrial equipment, industrial inspection gear, which goes into food factories, goes into pharmaceutical factories, and goes into beverage primarily. So for us, we're interested in things which can run from 24 volts and preferably, you know, the 36 volts, which some of the TI regulators allow us to do. Yeah, and I suppose we've shipped at least 30 or 40K of product, which is expensive product, but it's got P2 chips in there, and those have gone out the door. They've been out in the field for a few years now. So yeah, we you know, really like both the P1 and the P2, and we found it very robust. Every problem we throw at it, it does a really good job. So yeah, we're looking to. The other thing I should mention is we've got access to a SMD production line next door, like literally through this wall. We've got a friend who's manufacturing various electronic modules for the automotive and other industries, and so we've been keen. You know, this is the first serious board I guess we're going to be running on it in the coming week or so, but this is not far behind it. You know, so you know, just it's a little bit more compact than you know, uses more 0402 components than are usually run through that system, but it's theoretically capable of it all, and so we're going to see how we go.
Thanks, Lachlan.
Yeah.
Well, Chip, we could talk about the compiler, but maybe we should take a quick look and see if anybody has any support questions, if they're hanging around to have something important addressed to them.
I got a quick dumb question. I'm sorry. Late. It's Martin. Hi. Was that the P1? Or did I look at that chip? Or was that for the P2?
Lachlan?
You're asking about Lachlan's boards, right?
Yes. I'm sorry, I came in late.
Martin, it's the P2 primarily. It's a bit confusing because there's an adapter to the P1 socket, which means you can plug it into a system designed for a P1.
Oh, okay.
Yeah,
that seems quite interesting. Okay, I'd like to learn about that more later on. Cool.
Mm-hmm.
Thank you.
And Martin will follow up. He learns about everything we do.
Yes, I do.
He knows every person on our staff.
They're wonderful people.
Thank you.
You're welcome.
Other questions? People have any projects where they need some technical support help of any kind? This is the greatest collection of free technical support you can get. All right.
It's free.
Yes, more on P2 assembly language. How about a manual, please?
Yes. I'm in agreement. It just takes so much time.
Don't worry, just memorize all the instructions in your brain. Eventually you will go insane, but then you'll be able to write program.
Eventually you'll go insane. Please, on
You
that
see on
manual,
my funny
please.
camera here, I've actually something I've written. By written, I mean I hastily edited one of Chip's example programs that is actually doing DVI and VGA at the same time. It's very funny. Looks like you're
so you're doing, so that's DVI and analog VGA from the same program at the same time.
Exactly, and it's not even using any extra resource. Just have to like change the stuff around a bit. Can't really do anything else on the analog side because of how the sync sort of happened. But because of the way that the TMDS encoder ignores the bottom bit, you can make it work for VGA. I also have this forum thread for this stuff. I've also got HDMI audio going, but I'm not quite done with that. I have to actually turn that into like a usable something. But there's some demos in the forum. Can't show this because all of this is just doesn't do audio.
Hey, Skippy, back to you. Did you want to talk about the compiler?
Sure. Yeah. So last time we met, I was working on all this USB stuff, and I had this. I was having thoughts about the whole ADC thing, and I kind of spent a few weeks revisiting that. And I made some huge improvements to how we can acquire samples. Let me share my screen here. Advanced portion of screen. Okay. Where's my screen? No, it's not that way. It's this way. So this here is an 805 millivolt span. No, 805 microvolt span. The significance of 805 microvolts is that that entire range is one step of a 12-bit ADC or DAC. So you can see we're resolving maybe another, what do you think, 5 or 6 bits beyond that? If you average it, you get better than that, but these are just straight samples that are coming out. And but you see, this is probably 17 pushing 18 bits or so. This is a slow moving signal. Anyway, you can see these are microvolts expressed. So I added a thing to the scope, incidentally, that auto ranges, because I was having a lot of issues with things moving around as I try to measure them. So I just made a little auto scale thing in the scope. It looks like this when you turn it on. Let's see. Let's see. Oh, here we go. Right here. I just told it to, I want a channel called ADC. I want it auto ranged. I want it 400 pixels tall, starting 20 pixels from the bottom. And I want all the bells and whistles, meaning like the lines and the numbers. And then I want it in magenta. So that's what created this. Anyway, we can get pretty good resolution out of this thing. This, incidentally, is 3 pins. I could do this with 1 pin, but it would operate a little slower to get this resolution. Any questions about this at all yet? I'll show you how it works. Okay. Let's see here. Before I got on the meeting, I made some little diagrams. So this is of interest right here, this bit. So the way this is working right now, I've kind of come up with some best practices for how to go about doing A to D conversions. So it turns out, if you do little measurements, now I'm doing 3 pins at a time, right? But I could get rid of these 2 and just do the same formula on just pin 0. But I've got 3 going because if you notice, in any cycle, one of these 3 pins is muxing out to its external pin, and they're all tied together, right? So they're kind of teaming together to do an ADC operation. So in every cycle, one of them is measuring power, one of them is measuring ground for reference, and one of them is measuring pin. And by the time you get through these 3 cycles, you've done all 3 operations on each pin. The nice thing about having someone constantly reading his pin is it keeps the impedance identical for the analog source input. Because when you switch to like the internal VIO or GIO, which is power or ground, you then are not connected to the pin. So the pin doesn't see about 430K ohms of impedance. But this way, the pin sees a constant level of impedance, which is good for some reasons. It kind of keeps things quiet. So the formula I use here is this. I take the pin reading minus the ground reading, then the power reading minus the ground reading, and I sum them all up in this whole thing here. So I add all the VIOs together, I subtract all the GIOs from the VIOs, I add all the pins together, for this one here, and I subtract all the GIO readings from the pin. So I wind up with two numbers. And this forms a ratio that's, if you're between power and ground, it's going to be between 0 and 1, right? And so I do some math to keep the bits as like, what would you say, significant as possible. So I don't have any loss mathematically. But then I multiply that I do a Q fraction, I use the quartic. I multiply it by this huge number here, which turns that 0 to 1, which can actually go above 1 and below 0. But I multiply it by this full scale microvolt value. And then what I wind up is getting a sample that reads in microvolts, right? That's what we're showing here is, these are like microvolts, 6704 on the bottom and 5878, or excuse me, on the bottom. I think it was on the top. So this little math operation here, you can do this thing over and over in tight time spaces. But because you wind up with like a sample that is in microvolts, there's a lot of information in there that's kind of dithery, right? So you can sum these things together and keep getting better and better resolution, even though you're not taking like any different type of reading. I also made let me scroll up to it here. Let's see, where did I put it? This thing here, this thing that's called filter, whoops. This little bit of code here runs a filter which gives you, it's the way the binary timing works out, it's like a tree. Every other time through, it computes the divide by, or the average of 2 samples. Every 4th time through, it averages every 4 samples. Every 8th time through, it averages every 8 samples. And so it's like this tree, it's kind of a binary tree, and it always takes the same amount of time to execute, unless you get into these weird things only once every 64K cycles, where you can leave early because you're not at a filter level that you're going to resolve. You're going to ignore it. But this here does this like binary tree averaging. And so this is useful so that you can take these samples at very low resolution at high speed, but there's a lot of information hidden in them, right? That doesn't come out because you're looking at microvolts and you're getting at a high sample rate, a very, very noisy signal. But as you average those samples together, then they quiet way down and they become very precise at the expense of bandwidth. Let me go back down here again. So here's this. So, all right. So this is kind of the recipe. You take short measurements where you read in direct proximity, ground, power, and the pin, and then you perform this math on that. You wind up with a big number that's noisy, but the more you average at, the tighter it becomes. And I think because, and I'm using the Sync 2 filter, okay, which takes, when I switch, I have to throw away 3 samples, and then I'll like take a measurement that spans 8 samples. And it takes 3 because it takes 2 for the Sync 2 filter to numerically clear, but I have to go 3 because I switch sources in the ADC from, among GIO, VIO, and pin, and that pollutes what was going to be the first numerically clean sample. So I have to let 3 samples go by, and then I start getting pure samples that aren't polluted from the prior ADC setting, and I can make those as long as I want. And then and when each of those are done, I do this math on them. So I get these microvolt sample readings. Any questions about this?
I have one question, Chip. Are you doing all this on one cog?
Oh, yeah.
Do you have to use one cog, or are we using 2 to help you?
Well, you could do it on interrupts within the spin interpreter.
That's what I was wondering.
Yeah.
If doing the math, you using a separate cog would help make this even faster, or would it make it slower?
No, it would make it faster. So that was the next thing I was doing. So I got this methodology worked out, right? And I don't think I can push things any further. I can actually get down and resolve like 100 microvolt waveforms, which are 1/8 of what you saw on that display. But there's like a noise point I just really can't get past. I've tried everything, every trick I could think of, and I think it's just noise that's inherent to the design, and I can't get over it. So, we have about, let's say, 20, 30 microvolts of noise that I just can't overcome. Doesn't matter how long you sample for. That's just kind of our floor. But that's way better than we used to think it was, doing things the old ways. So when I got this code done, and I had this methodology worked out, I don't know what I could do to improve it. I think I've like hit the limits of what's possible. I started thinking, like you're saying, Grover, okay, let's put it in a cog and run it. We want to have, we want the user to be able to say how many pins he wants to do this for and where they are and all this stuff. And I started putting like, I wrote these little state sections, okay, like here's a thing that could read like 8 ADCs and do the differential, the sync 2 differential on them to track what's going on. And then it, 0 extends it because anything beyond that's trash. And then it sums. So it sums the measurements together. So it does this for a bunch of different pins. So I started writing all these like snippets that were going to, be required to realize these kinds of things. And then I started putting stateful stuff around these blocks. Like, okay, you have to loop this many times, and then you're gonna do it 3 times, and then you're gonna throw away those first 3 results. Then you're gonna do like 8 or so many, and you're gonna keep those results because we have to flush out the sync 2 buffer, and we have to allow the thing to settle to the new setting, the ADC. So as I started adding all that like stateful stuff around it, it's like really putting me in a box fast because it was ugly and it was just like arbitrary, and it's like not very flexible. And then I had this like huge idea. I realized what we could do to make these recipes is we could just build a bytecode interpreter, which just uses bytecodes to call out snippets that realize what we want to have happen. So what I can do is write like a general IO processor that can do ADC, DAC stuff, PWM stuff. It can, track frequency measurements and anything that the smart pins can do. They're always coordinated in real time, right? If they're not coordinated with other things, it often doesn't amount to anything. You have to have things working together. So what I figured I could do, and this is kind of what I want to work on next, is write all the snippets we need to realize everything of significance. And then I'll have a spin program which will compose a bytecode stream, which ultimately loops, that realizes your entire IO scheme. And when that thing starts running, you'll have a memory interface through hub RAM to all those things that you set up and put in motion. So this is going to be like really important. It's going to be, as important as the Spin 2 interpreter because it's going to be like Spin 2, but for IO. It will, and you'll be able to like call into this thing and say, I want this many of these. I want them to work this way. There'll be a few options. I want so many of these. And it will like build the thing for you by composing a bytecode program. And it's all happens at runtime. It's not a compile time thing. It's like an object that you'll instantiate that will do this stuff. And it'll build for you your whole IO scheme and turn that thing on. And if you don't have the bandwidth, you can start another one in another cog, right? You don't need to put it all in one cog, but as much bandwidth as a cog can accommodate, can hopefully, you know, you'll have to like use as many cogs as it takes. But I think for most people's applications, one cog is going to be more than sufficient to realize all this stuff. Because see, in the past, we've had all these little code snippets that do stuff, and customers are inclined to look at that and go, well, okay, I guess I'm going to put a cog on that job, and that cog will just sit there and spin on that function. But with a little breaking things apart, like some of these bytecodes are going to simply wait for the next time marker, right? Because it's like an RTOS in a way. It has to wait for the next 256 clock boundary. Then it has to have a bunch of short little conversations with the smart pins to get, you know, new data into them, readings out of them. And then in other times, it will then take that read data and it will like compute things like ADC samples or the reciprocal counter thing that we have in the smart pins. So it'll take care of all this stuff that any one of these things is complex to try to think about, right? But if we can have a system that automatically builds this and just gives you a memory interface, then it's really easy to like run a Gortzel thing along with, you know, a whole bunch of other stuff concurrently. Whereas any one of those things, everyone has to slow down, get in granny gear, read the silicon document, put something together, and then when they want it to do something else at the same time, they have to really start thinking hard. Well, I want to kind of automate that. So it'll make the smart pins completely accessible, as well as the like DDS and Gortzel mode of the streamer.
I just called Chat GPT. It'll handle it all.
Oh yeah. Well, I was hoping that would.
Okay.
Yeah, it won't be that simple, but like you see
Oh.
this here, this section here. What this does is this performs that equation I was talking about, where you take the you know, the signal over the full scale, and you come up with a number that's from 0 to 1, but might be a little under, might be a little over. And it's very Cordic intensive, right? There's all kinds of Cordic instructions. So the scale of economy is when you can do like, I found 8 of these at once. If you can do 8 of these conversions at once, it only takes 192 clocks, right? Whereas if you just do one of them, you give a Cordic command, then you wait 64 clocks for the result. Then you do the other Cordic command and you wait another 64 clocks. So you're already at like 132 with overhead. But for 60 more clocks, you can do 8 of those. You know, for another 50% of your time, you can get 8 of those done. So this is going to be the kind of thing that the bytecode deal will call. It can just run this compute samples thing, and it will like, you know, do this process as quick as possible on 8 ADC channels. And then this is hard coded. So I'll have some other bytecodes which can kind of shuffle the data around, because I don't have any time to make all this stuff indirect. So I'll have some bytecodes which can, you know, move little blocks of memory with registers around to support this kind of activity.
That is a good idea, using them, you know, creating a bytecode to handle all this stuff. That's a real good idea.
I'm excited about it because I always want to be able to have people use all this stuff, but it is, I mean, I have to slow way down to get any of it working. I have to go back and look at the docs, remember how it works, set it all up right. If that can just be automated and someone can call out, I want so many ADC channels at these rates, and I want these DACs on these pins, and I want Gortzel over here, and it just happens, then it makes all this stuff really accessible. You know, it lowers the threshold way down for what you have to do.
Lowers the frustration level too.
Oh yeah, yeah. It simplifies things. That equation, let's see, where did I put it? Where did I put, oh, it's all looking ugly because I got too many things in it. Let me get rid of this. This right here is the thing that does that, one operation on the ADC, right? To compute a microvolt sample, which has so much information in it in the noise that, you can add those things together and get good quality samples, but at a lower rate. But see, here's a Cortic operation, here's a Cortic operation. Those things take a long time. So that's what I've been working on in the IO. So meanwhile, any questions about this IO stuff before I go on to the compiler?
Is this code available?
I've put it up. You mean the ADC code?
Yeah, the code we're looking at right now. Is that available for me to try?
I'll post it when we're done. It's kind of a work in progress. I mean, you see, there's a lot of stuff I've commented out just because I'm trying to think like, okay, what's just test code ideas, junk at the bottom for notes. Yeah, I'll just post this. But when you run this program, it will make this happen. You just have to connect pins 0, 1, and 2, which are ADC inputs, to pin 8, which is being used as a DAC output, and you'll get this. I'll post it after the meeting.
Yeah, I'm just trying to follow your genius.
Anyway, so that's what I've been working on. So we got the ADC thing working, I think, as well as it can work. And there were just some things I didn't know, but about how to make it more efficient. I had to really get into it and suss out all these issues and come up with some way to do it. But I think now we've got something that's like going to take us as far as we can go with what the hardware can do.
Would you have to do this any differently if you had a higher input voltage range?
You could just make a voltage divider out of 2 resistors. You could theoretically even out of just 1 series resistor, but what I do, like on my on pin 8, is I come out of pin 8 through a 1 megohm resistor, and then I have a 1K to ground. So it's a divide by 1,000, right? And so that's why you're only seeing like 805 microvolts, where the signal's coming out of pin 8 at 805 millivolts. But I knock it down by 1,000 for just the purposes of testing. And I was using my function generator, but I thought I would go to the actual chip itself to generate an analog, signal to analyze, because that gets rid of any kind of ground loop. But I didn't really, it didn't really work any better. I think my setup with the function generator was pretty good anyway. All right, so the other stuff, let's see, okay. I'm gonna move over to the Spin 2 dock. Okay, whoops. All right, so here we are on the latest version. And so what I did, we had that bytes, words, and longs thing, which was useful for, I showed that last month, for just making a pointer to a string of data. It could be bytes, words, or longs. We renamed, because we wanted to conserve namespace. So we went back, like how I'd originally done it before I released it, just to using byte, word, and long instead of these names, which would have taken those out of the public namespace. So also there's this auto keyword to enable the scope to auto scale its trace data. Now here's something that Stephen and I have been talking about. He wanted, let me go back to my code here, because I had done a little bit about this down here. he wasn't really clear on, you know, how strings were working. So, okay, if you look at this case right here, at a very low level, the parser in the Spin2 compiler converts anything it sees as a string into comma separated data. So this happens way deep down in the parser, right? What Stephen wanted to do is just say, like, he just wanted to be able to say something like X equals ABCD, right? And let that become a long, like a long with 4 characters packed into it. Which we need to have something to do that. And I would love to have it just like that. But the trouble is that a lot of things in our language relies on this kind of like expansion. You know, it's a way to it's used in a number of cases. So,
and to clarify, Chip, if I may.
Oh, you're here, yes.
Yeah, I'm here.
I had forgotten you were here. I'm getting myopic because I'm only seeing a few people.
No, just to clarify, it's not that at first I wanted it. It's that I was trying to infer how things were working based on the fact that I was using single characters as quoted strings, and they were being passed successfully as a parameter to call, to a method call. And I was trying to infer what that actually meant without understanding that these strings were busted up when you do multi-character. And then once I went to 2 characters being passed, it didn't work. And so I'm asking Chip, well, what the heck? You know, what's the language really doing? And that's how we came to this discussion.
Yes. Okay. Thank you for filling that in. Yes, that's good. That's right. So I had to go into the compiler and kind of look around and think, well, could I just turn this expansion mode off in certain cases? But it turns out that we use this kind of expansion thing in a lot of cases that are all over the place. And it would create very weird rules if I changed it on a you know case on a method by method basis. So what I figured we could do instead, okay, this would be the ideal, but things aren't built in a way where that's going to work right? That's going to generate, you know, 4 different bytes and comma separated. So what I figured we could do, I was thinking, well, how can we then express, you know, up to 4 characters in a long? And I was looking around at ways to do it. I mean, I thought of using, because we have dollar signs and ampersands. Is that what that thing's called? No, that is the ampersand, the percent. We have these things that can precede hex numbers, right? And we've kind of overloaded this by being able to do double binary. But I thought if we see a percent and a quote, well, that could mean that we want to make a packed character long. Because Stephen would like to be able to use strings, you know, but have them just relate to one long, not actually 4 separate values. So Stephen, what do you think about this approach?
I think I can make it work just fine.
It's not as pretty as I'd like. I mean, I even thought of doing this, right?
Right, yeah.
But that's going to like cause conflicts with, you know what, the debug, right?
And so what took me down this rosy path was that I was looking at the, I'm working on the flash file system, releasing Chip's next version. And in the first version, we used the file open calls that are very ANSI C-like. And the second parameter is what mode you're opening the file in. As we added read, modify, write, the second parameter became 2 characters. And so, you know, in my innocent head of not understanding how strings were working, I was passing a quoted A, and then quoted R and W, and then I needed R plus and W plus, and so I just put it in there, and I get compiler errors, and I'm going, well, okay, why? And the error was wonderful because it says empty string when I pass a W plus. And so, what's Peanut doing? And so then I start chatting with Chip. Tell me why. Tell me why, what should I expect, what's happening? And that's what took me down this path. I'm not entirely sure we need the language extension, but if we use it this way, it could be used. I'm not going to have a problem with having a % quoted string. I don't know that we need this function and need to pollute up the space. What does everybody else think?
I think it's useful. You quite often have these 4-character magic values. It's kind of obnoxious assembling them by hand. So
It is.
have this, I guess.
Yeah, that's why I'm asking if we think it'll be useful.
Yeah, I think I have a couple of these that would be useful.
Okay. Then Chip, I'm okay with your % sign leader. I don't have a problem with it.
Okay,
We're
what
already
about
loaded with these things?
this? Would look a lot prettier, right?
Well, you've already got me parsing madness with definitions of single
The
ticks. Now
backtick
you're
sucks.
using-
No one likes the backtick. It's awful to type.
Yeah, and so
On my
and so-
keyboard, it's a one stroke.
On my
yeah,
keyboard,
it's
it's
one
like
stroke for most of us.
awful,
It's just
awful dead key. Makes sadness.
Well, see,
yeah, it's gonna be fun if we go backticks in not a great way.
well, I mean, this is really nice looking. I mean, we can't get any more elegant than something like that, right?
Yeah, we've got
This
a
is
little bit of
more-
language.
I actually
Agreed.
think the % sign is more sort of, I don't know, it looks more like, it makes more sense to me.
It's more
Yeah.
telling of what we're trying to
It
do.
kind of
that we're
makes
trying
it the
to-
number out of the string, and you know, it's normal quoted a single quoted character is already a character constant. So I guess the % makes it a multi-character constant.
Yeah, I
Okay.
vote for the % also. There's other languages that use precursors like that. The single
Okay.
quotes would I think it would confuse me more if I came along it later. We like confuse it with what a single quote would do or a double quote would do.
Yeah, it almost looks like some symbol or something.
Right.
Yeah, this is obviously string. Quotes around characters always means some kind of a string.
Right. So
Okay.
yeah, I'm going to be okay with the % invocation of this.
Okay, that's what I put in, and that's what I already released. That's in version 43.
Good. So let's call that good.
Okay, all right, good to have some resolution. All right, in fact, you know, Stephen, because you brought up that stuff that I hadn't even really considered before, I realized that we had some deficiencies in the documentation regarding this. I know other people think there are many other deficiencies, but this was certainly one. So
Thank you.
yeah,
A character, quoted age character. Thank you.
yeah, so what I did is I, explained that, what these things become. And so I said multiple characters in quote resolve to 8-bit ASCII values separated by commas. So this is what the compiler is going to see. This is what you type. This is what the compiler sees. Then I'm down here. Can you guys see my cursor by chance? Do you
Yes.
see?
Yeah.
Okay.
Yeah.
All right. So here we are with these new functions, right? So it's little endian and it's 0 padded. So like the case of 1, 2, 3 becomes this, where the 1 is in the least significant byte, the 2 is in the next significant byte, 3, and then because it didn't have 4 characters, it got padded with 0. Right? So that's kind of what that's the behavior everyone would probably expect, right?
I don't know if that. Hey, Ada, do you think that's forwards or do you think that's backwards or forwards?
That's the correct way.
Do you
I
like this
think,
packing
because
order?
if you put it in memory, then
Yes.
it's the right order.
Exactly. Yeah. The little
Yeah,
endian thing.
so as you stuff it in memory, it's going to be readable as what you expected. That's your goal.
Yeah, and in some cases you'd have to like write it backwards, but whatever.
Yeah,
Okay.
this endian business, once you're married to it, you don't get away from it.
No, I know that. I was just, what do I expect to see in it? Yep. Okay. I'm good with
All
it.
right. Okay, so that's that. So that, all right, that covers all that now. So we have some good explanation, I think, about how that works. Okay, now let me go back
What,
up.
excuse me, Chip.
Yeah.
What happens in the case if you go over 4? Does it just create another long, or does it truncate anything beyond 4?
No, the compiler stops and says, hey, you can't use this percent thing to pack more than 4 characters.
Okay.
It's a compiler.
Well, why
error.
not? You could make it like the normal strings. You could just have it start a new value every 4 characters.
We could, but what's the difference from just typing a normal string?
Well,
The
it's a
normal
value
string is
instead of
character
a
related.
pointer to a string, right?
Yeah. Well, you'd have to, what it would do is it would create multiple terms, which would have to be resolved on the left-hand side as well. They'd have to be taken somehow, you know?
Yeah, that has a niche use case, I think.
Yeah. I mean, we could expand it to do that in the future, and it would wind up creating, for every 4 characters, it would create a separate comma separated value. Right?
Yeah, that's what I mean.
Yep. Which is already what we're doing. It's a byte string.
Oh yeah, you're right. It's hard. I have to really think about the ramifications of that. It might be simple. It might be weird.
Yeah, I think, Chip, as you're thinking about it, ramifications probably should be explained a single character case. If you happen to create that as 2 characters, we probably need to fix that error.
Oh yeah. You mean how you're getting the empty string error?
Yes, because that makes
Yeah. I know what's causing that, but I got to figure out how. What I have to do is when you back up an element in the elementizer or the parser, I have to have it. I have to deal with
rich
the
enough to handle that.
information about the string in progress.
Yeah, exactly. It has to be rich enough to back up correctly.
Right. Yeah. It's not doing. It's not there. I don't know. I just never thought that would happen, but.
And then if we're done with string, I do have an observation here too. What would you think about identifying in the new keywords table there?
Yep.
Let's identify the byte, word, and long, and auto and percent text in that table. So we see
okay.
that version 43 is the first place that all of those are introduced.
Well, no, because they didn't. You mean the byte, word, long methods, right?
Yes, I do.
Well, here's the thing. Because they reused existing keywords and nobody used them as methods in the past, it's not.
I couldn't use the 41 compiler to get that behavior.
Right.
They would the code would not compile and generate the byte parenthetical behavior in 41. And so technically that capability arrives in broken in 42 and working in 43, broken with the wrong names.
Right. Yeah, I explained that it was actually introduced. Let's see, where's my cursor here?
Right. Right.
But you see that, though, that it didn't change the keyword base, right? So it didn't present a namespace conflict. So it doesn't really need to be gated.
I disagree in the sense that it created a new overload for the keyword.
It did that, yeah.
Yes, and so the overload.
Yeah, but what Chip means is that there's no possible code that would compile in an earlier version, but then wouldn't compile in the new version.
Oh, okay. Let me think about that for a sec, Ada.
You could argue that it's like good to acquire it anyways. So like you don't accidentally use something you didn't mean to use, or some sort of gigabrain thing like that. But
so what you're saying, Ada, to clarify what you're saying so that I know I'm understanding it, you're suggesting that if I did the byte parenthetical method calls, that just won't compile in 41 anyway.
Right.
So there's no expectation to it have compiled.
Exactly.
which tells me then that method overload, again, back to my thinking, that arrives in 43. Because we're discouraging anybody from using 42. So since it arrives in 43, I would add it in the 43 table as a reminder.
But if you go into, if you select spin, if you say nothing and you have default spin version 41, that stuff will still work, right? So you don't have to enable version 43 to get that functionality. It's there in every.
You're saying the byte, it would work in 42, but not 41.
Well, because the names got changed, right?
Well, no, you're telling me that it would work in 41.
Yeah. Well, if you set the level to 41, because remember,
works if you use the 43 compiler, but you're in 41 syntax level.
Right. So to get the new feature, yeah, Ada, that's also a confusion for me.
it's a victimless crime is what it is.
Okay, then if it's
But
a
it's
victim's
adding to
crime, how do I get the
understanding by
new
not
version of the
clarifying.
compiler?
What, Martin?
Where is the new version of this compiler?
Oh,
It's in the forum.
Yeah, if you go to the forum there and you go to that latest Peanut thread, it's at the first post in that thread.
Okay, thank you.
Yeah.
Mm-hmm.
Because see, the reality is you always have the latest spin compiler. You're not really running version 41 anymore. You're running whatever the latest version is. All we're doing is gating these keywords.
Correct. I understand that. That makes good sense.
Because there's going to be bugs that we're going to figure out and fix, and we're going to realize we're going to fix those, and that's not going to eventuate in any namespace change, but it's going to mean that people need to be using the newer compiler.
Yes, of course. Of course.
If you try to compile one with if you try to make a comment that says V45 or something, it should probably error out on that if you like just flat out refuse that, because otherwise you get a weird error somewhere down.
Okay, so you guys, this business here, we've just added. Someone today was saying it'd be better like that. I don't know how you guys feel about that. Putting a dollar sign. I think that, it literally looks for left curly brace. It doesn't care about case, but it looks for spin 2 _ V and then 2 decimal digits. That's what it's looking for. And then a right curly brace.
Does it, well, with how many versions there are, I'd probably check for more than 2 digits.
Yeah, I'll show you. I made a little bit about this down here. Let's see. Okay, here we go. Spin 2 version selection. This is the part of the doc that talks about this. So the deal is if you say nothing, it'll be like saying version 41. So all you're missing is the L string, right? If you say 43, then you get the L string. If you say 99, well, the compiler may not be, there is no version 99 yet, right? But let's say we're at version 44. It'll go down and go, well, there is no 99, but we got the 44. You want to go high? Well, 44 is the highest we can do. So it will be like, so this is a way to kind of like say that, always give me an error if there's a namespace conflict. Does that make sense?
Or does that hide it?
I would just rather have it error out if you do that.
Yes, if it's a version
version is lower than 99, this compiler is too old. Please don't.
Well, but I wanted to make it so that someone could kind of future not.
That sort of defeats the purpose. If someone leaves that in, it will break again.
Yeah, well,
that's sort of like stepping on a rake, but
right.
You don't have to leave the rake lying around.
Right, but the thing is, if someone wants to always know if they have a conflict with the latest compiler, that's how they're going to find out.
Well, they can
But
just,
that would-
couldn't they
you
just
would
put in the
never-
version number of the latest compiler that they have.
Yeah. Chip,
Ah.
I think the danger is right now to further explain what Ada's saying is that you wouldn't want to put under version control or in the P2 OBEX or P1 OBEX anything with a V99 directive in it.
Oh,
Because
yeah.
then from then on, that OBEX object is going to be broken.
I
And
see
so-
what you're saying.
So don't let that show up in code and be treated. You can, in your latest, don't put a version number. Oh, your fallback. In your latest, you'll always want, if you really want to use something in your local code that is the latest, then let us specify the version that is latest.
Right.
Don't let us create the situation that got us into the problem in the first place.
I got you. Okay, so I should only accept actually known versions.
When you see the signature, yes.
Okay.
And
so
everything else cause an error.
Okay, so this means that if V41 is the default, right? Because that's where we're going to say that's
Yes.
where the time point is. If they
Yes.
say V42, but V42, yeah, it existed, but
Broken compiler.
nothing changed until V43, then what that means is that they're only going to be able to put in versions which introduced new keywords.
No, I don't think that's good because sometimes it might change in a way that you don't need a new keyword, but maybe there's like a bug that's been fixed or something. So you could indicate that with the versions, right? Because there's always some sort of change. It's kind of just useful in the sense that you say, well, this is the compiler version when I made it. It works there.
Okay, even though there might not be any new keywords.
Yeah.
Okay, well that's
Right.
kind of how
it should just the only thing it shouldn't do is if the current version is higher than what the compiler is, then it should
okay.
probably complain about that.
Okay, that's the only check. I'm going to move down here. Look at this real quick. Okay, here's like a minimal program, right?
We lost you off screen. There you go. Okay.
Okay, so if I do a Control L to like list this, it says version 42, right? Or excuse me, you see this here? This is part of the list file now. Okay, so I'll go back to the source.
Okay.
I said 0, right? And it resolves to 41 because it goes, well, 0 doesn't exist, but 41 is as low as we can go. So, but and then look at this. If I say 40, like 41, it's same thing. If I say 42, then it really goes to 41 because
42 should not exist.
well, 42 didn't introduce any name change. But I need to be okay with that. So what I need to do, I need to change the way this thing works a little bit. I can go V43 and it knows V43, but if I go V44, it's like, no, 43 is all we got. So basically I have to filter those numbers between 41 and whatever the latest is, and don't permit anything else, right?
Right.
Okay.
And then if we try and Ada, if we specify something that's not feasible, should that be an error or a warning?
What do you mean?
45 is released. We say I want 47. Is that a warning or is it ignored? Does that make sense? Did I say that too tersely?
Because the
said,
audio is bad.
Yeah, if we try and specify a version that's beyond what's new, is that a warning or is it ignored?
Well, that should warn, of course, because as I said, if you don't do it, you will get some sort of error further down where it's like, oh, there's this
Agreed.
keyword that was used and it doesn't know what to do with it. Or maybe there wasn't a what I think is that the way there isn't a keyword change, but there's some sort of other functionality change. And like the address shifts around or something.
Yes.
And you might just want to have it for that sort of thing. So
Yeah,
Yes.
so we want to log version numbers that didn't have any namespace changes, just because you want to know, it just might be useful, because in that version, maybe some new feature was introduced, but didn't have a namespace change.
Yeah.
But
I mean, you
might
could have
be
a binary
important.
compatibility issue even. Yes.
Right,
Yes.
right,
There are
okay.
lots of reasons to track it.
Okay, so we're gonna permit from V41 up to whatever the current is.
Correct.
Okay, so this means if someone tries to compile a program on an old version of Peanut or the compiler, it'll actually just error out and say, hey, that version doesn't exist, cannot do it. So you need to be using a modern tool to compile a modern program.
yeah, you mean you can try just removing or changing the version that's in the file if you really need to, but I think just having it not do that by default is pretty useful.
But
Okay.
you guys got to protect me from myself. So if I'm not aware of this, I should be flagged.
Yeah. All right, so how about this issue here? Someone, Electro Dude, I think it was, said that he'd like to see a $sign just so that he knows. I mean, I do require all these curly braces. It can't just be, I mean, this wouldn't work, right? That's not going to do it. It has to be like this. So do we need a $sign? To me, it looks just kind of extra.
I don't see any reason for it. He was thinking it was creating a variable that could be interrogated, I think. Was I reading that correctly?
I don't know.
I think the problem is if you introduce comments like this, well, like they could sort of eventually conflict with actual comments.
Correct.
I don't think that's particularly a thing, but
yeah, well, see, if that was the case, I'd be inclined to just do something like this. You know?
Yeah, nope. I say let's keep it as the way it is. It took us a while to get here.
Yeah, I think just leave it. Just don't change it again. It's
like
fine.
This.
Just don't change it. Just leave it be.
No $sign.
No.
I know this seems to be like the most difficult thing for like software engineers to understand. Do not change the software. It is good as it is.
Yes.
But they don't understand. They keep changing it.
We like to change things. Okay, so all right, so I'll constrain the expression of version numbers to fit only known versions.
Right.
So that way, if someone said we're 45 and they try to run it on a Peanut version 44, it's not going to compile it.
Right.
Okay.
Maybe too.
Okay.
I'm
All
okay
right.
with it.
Okay, well, what I'll do is that's kind of a subtle thing. So I'll introduce that actual behavior because nobody knows the difference at this point. I'll introduce that next behavior in the next release, along with whatever else is in there.
Okay.
No one's going to realize that these subtleties, you know, it's kind of all under the radar right now.
Okay.
But what I'll do is I'll change my documentation around to express the intent that we're talking about.
Good. So we all believe that behavior, and then it'll roll in under us correctly.
Right. Right. That's right. Okay.
And then I'll do the same thing in the VS Code document generator, like you're doing with a list file. I'll do the same thing and emit the version number out when you generate the document.
Okay. Oh yeah. Yeah, it'd be good to have.
So Chip?
Yeah.
Did it specify in the documentation where this particular specialized comment should go?
Yeah, okay.
Please.
Yes. Before any spin 2 code is actually expressed, before like you have any block statement or any assignment or anything. So what it does is the way it actually works is it calls the parser because comments, if all a line is a comment, the parser just returns an end of line, end of line, end of line, end of line, until you get to your code. So before the code, it has to appear somewhere.
Anyway, is that, as long as that's specifically called out in the documentation, then.
Yeah, what did I say? I said the compiler searches for the string comment before any code is expressed in the submit2 file.
And something I like to do sometimes is actually having an object block at the very top and just using that for
Somebody's talking over us here, Ada.
I got him. It was
Thank you.
It was David. I just I muted him. He can, I think.
Sorry, Ada.
Anyways, what I sometimes like to do is have an object block that doesn't do anything at the top, just to get that nice red color in Propeller too.
Yes. Yeah.
And I put all my comments in there.
Oh, that's a good idea. Yeah. Now that would blow up code though, because con is the first default block.
Yeah, that's kind of.
We could just make con sections red.
Hey, Ada, I finally got the con recognized
no.
as the first default section.
Oh, it finally works. I think there's like a trillion pieces of code that actually rely on this.
I know. What can I say? It took me a while.
Oh, I wanted to show you something. You know that filter I was talking about, how every other time it generates an average of 2 samples?
There's your tree, yeah.
So see here, these are like the samples that are occurring. Boom, 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 boom. These are all the samples coming in. Every other time, you're going to compute the average of 2. Every time in between those, you're going to compute the average. Well, this is like 4, right? It's a power of 2. It's 2 to the 2. And here's 2 to the 3, every 8th. And then every 2 to the 4th, every 16th. And this pattern, it just goes on forever. You can have as many layers as you want. And it's a funny thing because the code that executes that takes the same amount of time each time. It's like a dozen instructions or something. And it will compute every power of 2 filter.
Yeah, it's a sort of, I'd say it's an octave, right?
Yeah, octave. Yes, yes.
Yep.
And the way it worked was just taking the counter and bit reversing it, and then doing an encode on that. And then you come up with this. You come up with who you got to service next, which one you're going to compute. Anyway, I'll stop sharing here. So those are the changes in the compiler. Let me make sure there's nothing else to just mention. No, that covered everything.
Right.
Too bad Eric Smith isn't here.
Yeah, it would be funny if he was here, but
he'll watch this.
We're just putting work on his plate.
Right.
But we can all lock down on the same solution now. That's nice.
Yeah, yes.
So
Yeah,
thank you for that.
Well, thanks for pushing me to do this. I mean, I realize, yeah, it's something that's good to do because it just creates safety and doesn't kill code that already runs.
I think the HDMI demo comes with the Peanut is actually broken.
Oh, okay. I'll go in there and look.
Maybe that's a bit of a dubious one.
Broken in function or broken in keywords?
Broken in keywords because there's of course a label called field.
Yes. That's interesting. I didn't even notice that. My highlighting test should have figured that out.
I mean, I can, if there's nothing else, I can talk a little bit about the HDMI audio because it's funny.
Oh, yeah. this is a big deal because if you can get the HDMI, if you can get the HDMI to handle the audio, then you don't need separate connections for audio. The TV or monitor can be your speaker.
Yeah, it's just currently I'm obviously still having the DAX active for like thing, but for like basically for timing. Because but you could use a normal timer for that. Actually, there's one where I don't have the DAX active, where it's just generating audio and the video code, like a sine wave for like the funnies. Where do I have the thing? Where does the code go? Why is it always missing? Wrong directory. If you have a lot of similarly named directories, you eventually die. Where's that?
Kind of becomes searching for files instead of using files.
I've got maybe it's this one. One of them. It's gotta be one of them. No one knows where I can just searching for the one to run it. You won't hear anything anyways because it's all like I don't know. But it's nice to have the to have it at least running. In theory, if I can actually is this what the one that has the funny? I don't know. No, this doesn't have. This is not the one with the drop meter. Is this the one with the drop meter? Because that's more interesting. There's still image. Yeah, that's the one with a drop meter. So the thing with these HDMI audio things is that they have these deeply curious packets. If I can find where the PDF file went, I don't. PDF files disappear. So this is the documentation they have for the audio packet.
Mm-hmm.
Deeply confusing. So what actually, I guess I have to show the other graphic first because it makes no sense otherwise. So this looks like some sort of astrology chart, but it actually tells you how the packets are sent. So on the channel 0, which is the blue channel, it just sends bollocks, and also the BCH block 4, which is the packet header. That's 3 bytes of a packet header that you can send. And you get, using the red and the green channel, it sort of sends these 4 what it calls sub packets, which are 7 bytes each. Of course, there's always an extra byte at the end for checksum. And so how the audio packet works then is the packet header tells that it's an audio packet, and also tells the TV how many samples are in this packet. And then you just have this sub packet. Each sub packet then encodes 1 sample, which is 24 bits and 2 channels.
Mm.
Dubiously, it also has all these status bits and the parity bits that you'd get from an SPDIF connection. You just put those in the last byte here for reasons that I don't quite understand. I don't even know if they're used for anything. They're just here.
What's the nature? Is it an easy answer if I ask you what's the nature and difference of SPDIF versus this?
Well, the SPDIF it isn't packets; it's just samples that are getting clocked out, and the SPDIF is just on its own link, right? And this happens sort of inside the blanking area between the video scan lines.
Oh, interesting.
And that's why it's packets that are sort of discrete and can be slotted in, and they can have 4 samples each. So you really never need more than 2 samples, because if you think about it, your VGA is the minimum resolution, right? That has like a 31 kilohertz line rate. And if you have a audio signal that's at one of the rates that's supported, which is 32, 44.1, or 48,
Right.
there's always either 1 or 2 new samples.
Gotcha.
As you can see from this bizarre display here, maybe no, you can't because the camera is shit. Sometimes it actually ends up with 0 samples, which is kind of strange because of the way that it ends up generating the samples. Because what this one is doing here in the background is it's actually taking from the Yamaha sound chip emulator the samples, and they're coming in at some bizarre rate, like 53 point something kilohertz, and it's doing cubic interpolation to make it 48 kilohertz.
Oh my gosh. Okay.
It's actually a very small part of the processing. This big brownish one that you can see here that's actually the encoding of the packet. Because it's kind of bizarre how this, you see how these bits here actually are encoded, right?
You're using some of the display to tell you the frequency of when certain methods are running.
Yeah, that's well, not methods, it's just sort of sections of the code.
Okay, yeah.
Cool. And it has to run each line, right? So it's easy to display it that way.
That's very nice.
So it has these 7 bytes here that you have to encode per sub packet, and those 3 bytes for the packet header. These all, and this becomes 4 bytes because of checksum, and this becomes 8 bytes because of checksum.
Okay.
So the first problem is you have to compute this checksum, which isn't really a problem. It's just that they explain it using this one paragraph and bizarre graph. Right?
Yeah, I think you're.
What the fuck is a syndrome?
Exactly.
I don't know. It's just a CRC. Don't think about it too hard.
1, 6, 7.
If I can find where the code is, it's literally just.
It's the powers.
Yeah, all
I don't
this
know.
CRC stuff is always like backwards and inside out, and never what you think it is.
I know. Well, they call it a BCH error code correction parity, which I think it's a special sort of CRC that they can use to sort of correct bit errors. Like they chose the polynomial in a way that they can figure out where the bit error happened.
Sure, that would make sense.
But it's really just a CRC. You don't have to think about it if you're sending it. So right now, this is now back to the astrology chart, right?
Yes.
So of these 32 bits of packet header, we so the packet itself is 32 pixels long. And each channel for each pixel sends 4 bits. It's not using the normal video encoding, it's using special encoding. So each channel sends 4 bits. The blue channel, the LSBs, are sending HSync and VSync for when you want that to change during the packet for some reason. I don't know.
Ada, you're saying that when you're doing audio along with video, the video even gets encoded differently?
No, the video is basically as normal, though there's something to talk about with that as well. But the basic video encoding stays the same. You can just use it as normal.
Because this all happens in the blanking intervals,
This
right?
happens in the blanking interval, and there's some stuff that happens around this. I'll talk about this later, but the actual packet is encoded like this, right? You have 32 pixels, or characters as they call them, and those are selected from a table of particular raw characters, which is this one. So that's your 16 possible values that encode 4 bits per channel per pixel. And then you have in the blue channel, you encode HSync and VSync, the packet header, which is 32 bits, and this fourth one, which doesn't really do anything, it's just a sort of start bit. I think there's a separate chart that shows this. And then using the other 2 channels, so you take the bit 0 from the green channel and the red channel, and that sort of 2 bits of the first sub packet.
Jeez.
So at the end, you end up with 64 bits for that sub packet. But then bit one from both of these channels becomes another sub packet that's completely separate, and they all combine. One optimization that I haven't really done yet, I was looking into to sort of cut back on the encoding time, is that when you're doing the audio, remember you only ever need 2 samples in a packet. There's never a situation where you need to send more samples unless you're doing something non-standard. You could actually just ignore all of these bits here. But I haven't done that yet. And you can't fully ignore them because you do need another type of packet. This isn't the only packet that's needed. The audio packet that we can see down here, that just has the samples and the nonsense in it. We also have this thing, which is called an audio clock regeneration packet. And what this is basically just because the audio is just sort of coming in packets. This sort of helps the TV figure out what the actual sample rate is that it should be playing those back at, because you want them to play back at equal intervals. And sometimes you don't quite know at which rate these audio is coming in. Like if you were to maybe make like an SPDIF to HDMI converter or some sort of thing, right? You don't really, the samples just sort of come in over the SPDIF and you can't really know what the actual speed is of them. So what this is designed to do is you just count how many samples come in a particular number of pixels on the video bus, and then you send that in this packet, this information. Now, of course,
that causes it to pace out the samples on playback.
Exactly. So we're generating them at a fixed sort of clock ratio. That everything's on the same clock domain, so we can just pre-compute a packet that for this. Because it's never going to change. You can just compute this because you have both the number of pixels that you're counting over and the count are both user-defined. So you can actually work out an exact ratio that will be exactly perfect.
Wow.
And
so is it repacing the audio samples as it plays them then? You're not feeding them to audio as they arrive.
Well, I'm sending them out as soon as possible, of course, in the video driver.
Got you.
But the TV sort of receives 2, 1, or 0 at a time.
Got you.
And
it's using this information to pace it properly so the audio sounds correct.
It has to buffer a few to make that happen.
Yep.
And that's how it figures that out.
And this happens in every horizontal blanking, right?
Yeah, it happens. You can technically, it doesn't really care where you put the packet. It just has to be in a blanking area, of course. And there's all this stuff around it. If I can find where this is the one. So look at this diagram. You need this thing. It's called a preamble. This is just a normal blanking thing happening on channel 0. But you need this preamble on the other 2 channels. And to sort of tell it, oh, there's data coming up. And then you need this thing called a guard band, which is 2 characters long. And then you need the packets back to back. You can have multiple in one sort of island, they call it. But what you have to take care of is that this top bit of channel 0, it's kind of like a start bit. It has to be 0 once, and then it has to be 1 all the time. Then you need another different guard band for 2 pixels. And then another thing is, as soon as you have any of this packet stuff going on, you must also have a preamble and a guard band in front of the actual video. But a different preamble and a different guard band.
Interesting.
you don't have put one after the video, but you have to have one in front of the video. And something kind of bizarre that happens is if you send the video guard band but never any packets, this actually confuses pretty much everything I've actually plugged this into, and there's like a pink bar that shows up.
Wow.
So it actually needs the data period to actually be there to sort of notice, oh, this is a proper HDMI signal, we have to cut out that guard band. What the point of it is, I don't know, but it just has to be there.
Wild. It's an 8-character preamble in both cases, 2-character guard bands, 2 pixels.
Yeah.
Sorry.
Well, characters, they call it characters.
Okay.
Because, but we can.
But we think of it as a
technically,
pixel time frame.
sometimes a pixel might be multiple characters if you're in deep color mode.
Okay.
Like if you're in 48-bit mode, obviously you need 2 characters for each pixel.
Gotcha.
But there's also like some bizarre thing if you just need like 30-bit mode that doesn't really fit into characters neatly. So there's some Byzantine system of packing that into the characters. By the way, modes, you can also set different modes, which if I go to the upgrade available Ubuntu on 23.10, this version will stop receiving updates and security fixes in 37 days. Well, that's a interesting rancid note there. I love it when my computer is putting like it's like doing these things. You can also put packets on the bus that make it I say bus, it's not a bus. You can't plug multiple into this.
Sure.
You can put packets in the signal that switch it into different modes. This is called YAV test. Is this correctly set up? Yes, it is. Maybe it will get a picture. I don't know. You may notice that the colors are weird, and that's because it managed to switch the display into YAV mode. So you're now getting a component sort of color signal instead of RGB. And you get that by sending a packet that does it.
Jeez.
There's also deeply dubious a 422 mode with chroma subsampling. But the way that's packed makes it sort of not very useful for using on the P2.
So overall status, where are you with getting this working audio over?
Well, it works, but it's not really integrated in like a serious anything yet.
Okay, so proof of concept working.
Yeah, what I still wanted to get
reshape the code
working is SPDIF simultaneously. But the problem is there isn't really enough time in the scan line to do that.
Oh, to like compute CRCs and things?
No, it's actually the sort of biphase mark encoding for the SPDIF output.
Oh, okay, gotcha.
I can do the SPDIF on its own. And so the idea there was because I'm already sort of doing the interpolation and all these sort of conditioning to create a nice digital signal with a normal rate. I thought I might as well just have the SPDIF output as well. So you could use it if you just have analog video or monitor doesn't have audio, you could still get a digital audio out. And I thought it would be basically free, but it apparently isn't. I have to make one maybe where it uses the optimization that I talked about. Because actually generating this packet is kind of the longest part. Calculating the CRCs isn't so bad. But actually just generating all the 32 longs that encode the data, that's actually where most of the problem is. If I can find the one again that has the graph here. So the packet, and why is it green now? I think it didn't properly reset. It's still in YAF mode or something. Yeah, there we go. So this red brown sort of part, that's actually how long it takes in terms of the scan line to encode the packet. And I think this one doesn't have any of the SPDIF in it right now. But the SPDIF takes a really long time too, because while it's doing all of this, we're doing a 320 by 240 mode. So we actually have to stuff pixels into the streamer all the time because it's too stupid to repeat them itself. So you always have to repeat each pixel twice. So it kind of limits how fast you can do some things because you constantly have to call into this other function to do it. To the pixels. This doesn't really matter much for this stuff, but you could do the biphase mark thing with a really fast loop or like a skip sequence. But you can't do it with this, with that limitation of having to constantly do the other thing. The other thing is that
interrupts don't help because it still takes time away from you.
Interrupts will take even more time because
Right, that's what I was thinking.
Because you can do an underscore ret to return out of a function, but you always have to do an iret to return out of an interrupt.
Right.
And the other thing is that you eventually run out of memory with all the stuff going on. Now, I haven't really compressed the driver that does this very well, but it just sort of ends up running out of memory eventually. With just all that code in it. That's probably, can probably make it fit in the end by using some more of the LUT area. But, you know, of course, half of the LUT I want to keep free to load the palette into, right? We need a space somewhere for the to store our audio reclock packet because we don't necessarily want to have it in hub RAM. We could have it in hub RAM if we could rely on the hub RAM, but I want to eventually put this into the funny emulators, and those, and with the Neo Geo emulator, it will eventually just wipe out all the startup code, and you can't really find that in hub RAM anymore, unless I make a separate buffer area for it somewhere deep down in. It's very, very confusing everything. For buffering one packet is like 128 bytes because we have to put it together in advance with 32 bits per character because it can't really encode that directly. But that's something that would be kind of useful in some sort of future P2 revision, is having a streamer mode that does this directly. Where you give it 16-bit words maybe, where each nibble encodes one of the channels, and then it sort of maps this directly onto those other ones. And you also have to map that hsync bit into bit 0 so that the other thing keeps working. Very, very complicated, but it would be kind of useful to have that. I don't know if this is like there's like a patent on this nonsense. Like who knows? Maybe they have one. Maybe they found one laying on the floor.
Is this document you got, is it just available on the web?
Yeah, you can just find this. This is slightly old. This is the 1.3 specification. I don't think they have a newer one. And there's no like weird watermarks and disclaimers about this being sort of like a highly confidential document or something. So I guess they just posted it somewhere. It's like from 2006.
HDMI 1.3.
Unauthorized use of application prohibited. Wait, You posted it to the internet, my friends.
Yeah, really. Like, wait, what?
Significant new features, Type-C mini connector.
Special.
Actually find the deeply dubious Type B connector, which is
A, B, or C. TMDS.
actually have to. There's a Type A receptacle. That's a Type A plug. That's a Type B receptacle. Ever seen a Type B receptacle on anything? Ever seen a Type B cable? No, because it's like weird and doesn't exist. It's like the HDMI equivalent to a dual link DVI, but they just never made it. They just put it in the spec. And it's like technically you can do it, but no one has actually done it. And you can't even buy the connector for it. So like, why? Because the problem with this connector is that it's a different shape than a normal HDMI connector. You can't just plug the Type A connector into this. So it's just pointless, because with the DVI you can plug the dual link cable into the single link port, right? No, this doesn't do that. It's just stupid. Amazing attention to detail there. And then you have to like quote unquote new mini plug. I think they have to micro plug at this point or something. I don't think they talk about MHL in this one, which is also a deeply stupid thing, where they tried to make like HDMI out of phone, but they were too lazy to actually put like more pins on the phone. So they just use one of the channels to put the entire pixel through, because they realized if they can do like super high resolutions on the TV, you can do like a normal resolution signal, but only on one channel. But no one ever supported it, so it died. Amazing, right? I don't think it talks about this one here. Okay, that's your amazing encoding table.
What's that coding?
It's called TMDS error reduction coding. That's what's used for the data packets.
So you send the 4, it implies the 8.
No, you send these 10 bits.
Oh, you send the 10 to imply the 4.
You
And
send
so
the
you
10
have
bits
the
and,
redundant
and
bits
these
in
really
there.
4 bits.
Gotcha.
But this is not a nibble. This is actually treated as 4 separate channels that are sort of transmitted simultaneously.
Gotcha.
And that's just for control data, not pixel data, right?
This is for the auxiliary sort of audio and other stuff. The control period is what the H-sync, V-sync sort of stuff. That's control data. But it's also just using each channel to transmit sort of to transmit 2 bits.
Is
and
this
for
the
the channel
same?
that's H-sync and V-sync, and for the other ones that's used for the preambles and I think some other nonsense.
Is this
No.
the same data that is covered by that polynomial you showed us?
By that what?
That equation for your parity bits?
Oh yeah, is this already like run through the CRC?
No,
The CRC
CS
would come later, right?
No, the CSC comes first, and then it's sort of assembled into this encoding, this line codes.
Oh, so that stuff gets subject to the CRC. The bigger word size.
No, the small one gets subject, but it doesn't subject like this as a 0001. It's actually like this bit, this bit, this bit, this bit, this bit, this bit, this bit. Like it's using the lowest bit of each for one, and for the actual sub, that's for the header. It works like that, but for the actual packet, it takes the even bits from the green channel and the odd bits from the red channel. But they're sort of the CSC computation happens in the logical order that they that they should be in when you reconstitute everything.
Wow.
Jeez.
And that CRC, of course, gets appended onto the data.
So that
Mhm.
CRC needs to be computed on a bitwise basis.
Yeah, it's
From by selecting bits within lists of words, right?
basically that, but since I actually do this sort of bit interleaving later, I just because sort of each bit position sort of turns is in itself a packet, a sub packet, which, as we remember, it looks like this, which has bytes in it that have like some sort of meaning. It's easier to treat the sub packet as 8 bytes, compute the CRC into the last one, and then sort of interleave them together, the 4 sub packets and the header.
Split them out later for transmission. Okay.
Deeply dubious system that they came up with.
Well, it's like only hardware. I mean, it's like, I don't think they thought software would ever be up to speed to deal with that anyway. But I mean, they made something that like hardware description language has to
right
be
it's
written
probably
for
nice if you
deal
have
with.
a hardware description language, maybe. I still don't know if interleaving the sub packets like that is a good idea. Maybe it helps with the error correction. Maybe. I don't know.
Sure is complicated.
Yeah, it's kind of more complicated than it really needs to be. I think they could have made it a lot simpler and, in fact, sort of solved some of the compatibility with DVI devices more elegantly. If you just left channel 0 using the normal control bit encoding, and then you just encode 1 byte at a time using the other 2 channels. They sort of you sort of have to put the header in with the other stuff, but like, come on, there's so much space. You don't need to be so like there's enough space for normal audio, and if you're doing like really weird stuff, you do have to increase the clock anyways. If you do like want to do like 8-channel DSD or something, which yes, you can do, that's part of the spec. You have this 1-bit audio sample packet where you can put your DSD data from like an SACD player in, which is deeply mental. But that may actually be the only way to actually get digital anything out of an SACD player, a normal one, because they're crazy about the copyright on those things. So, and there's no normal interface that takes this sort of data anyways. So what I think happens is that HDMI with the encryption enabled is actually possibly one of the only ways to get pure DSD between 2 devices from an SACD without any sort of like hacking. So that's interesting. You can even more interesting is that it supports sending DST data, which is even more bizarre. Why would you want to send DST data? Why not just, if you're generating DSD data from somewhere, you can just decompress it. Why this? Does anything even support this anyways?
DSD audio streams.
Very interesting. Of course, you also have this high bitrate audio for like other compressed formats, completely different. And if you just want like normal compressed formats, you'd actually do that with the normal audio sample packet, because it's similar to an SPDIF packet, and you do the exact same thing that you do over SPDIF if you want to put like a Dolby AC3 into there. Which is, that's also another one of those bizarre things that you can do, is send compressed Dolby AC3. Why you'd ever want to do that, I don't know. Over HDMI anyways, but you can do it. It never works anyways, at least not with the TV I have. It's too stupid. It can't pass it through back to the audio box. So what's the point anyways? You just have to connect it up directly, and then it works, and you can get your stupid AC3 compressed audio from like a Blu-ray or whatever. They still have AC3, even though they could probably just do discrete audio on a Blu-ray, but what do I know? They probably have like 1 trillion different formats on these, just because there's all this sort of patent and there's different competing formats. It's all very, very strange. And down here, there's more details about how the audio actually works. In particular, about how you might use the those CTS and N parameters that you send in the clock regenerator packet. It's actually a recommended optimal value for N, allegedly, and of course, CTS you'd have to actually just compute. CTS is basically free form. And there's a number of CTS and N pairs that will have exactly the right rational relationship to when you can say, I have this many P2 clock cycles between samples, that you can say I have N samples in CTS HDMI characters or pixels. In this case, it's also about characters because, of course, deep color, blah blah blah. What matters is the clock that comes out on the actual connector. Every time that pulses, counts for one of these, and every time there's a sample, it counts for one of these. You can see that's sort of what's the other way around. I think it's the other way around, or maybe my brain hurts. Anyways, that's the values that they are normal. But you can just put your own in, it will work.
Interesting.
But I say it will work in quotes. Apparently, Roger on the forum says it doesn't work with any of his stuff. He's got like a weird TV and like a weird audio box. They don't like it. But all the other guys say they like it. I don't know if you have one. I can link the post that has like the latest demo for this. Where do I have that? Yeah, there we go. Let's give me the permalink. I will put it in chat. I will put in chat. So you can try that at home and see if it makes any noise. You have to change the pin in the driver file. Just don't think about it too hard.
Sorry about shaking my camera there. I was typing.
Is there anything else silly? I mean, there's a bit of silliness regarding the resampling. I think this is the current version. I don't know. I don't know what the current version is. Maybe I'm silly and stupid. Well, this certainly isn't, I don't think. I think this may be the current version frequency plot of what that ends up looking like. Oh no, it doesn't find my window because I have too many windows open. Why is this? Why is anything? You need to install Pulse Audio 1.0 and above to support audio share. That's not what I care about. Also, like, isn't everything Pipewire now? Isn't that the new thing? I don't understand. Can you please give me the window that I want to? Oh, I think it did it. Look, this is what a graph looks like. That's the graph of what happens if you put like a sine frequency sweep into the cubic interpolation filter. As you can see, it generates garbage frequencies.
Interesting.
The problem is if you do not filter it at all and just pick the nearest sample, it looks like this. Yeah, and if you sort of do a linear interpolation, it looks like this, which is still not very nice. And if you had one that didn't suck, it would look maybe like this. What it should look like is like this, maybe. Actually, it should cut off at some point because that's the raw version, and that's like the version when you convert it. There needs to be a bit at the top where it sort of goes away. And there's a number of interesting
what's that?
graphs that I made while figuring that out.
Ooh.
It's got to do with the sync function. I initially thought I'd use some sort of sync thing, but it turned out to be very complicated and slow. And the cubic actually ended up working kind of better. So I don't know how that happened. And yeah, it looks like this. It's currently used to bring down from 53 something to 48 in the OPN2 test program that I wrote, which uses OPN2 cog and just plays music into that. I've also had one that took one of the other ones, the SPC cog, that puts out straight 32 kilohertz, which is a directly supported rate. So you can just put that in without any of the sort of interpolations. And that was the first thing I got going. You can find that earlier up the thread. But if you had a differently odd rate, like you had, I don't know, 46 or something, it's just something nasty like that, you could also use the same code to upsample it to 48, which would be better. Which would be better than just leaving it as 44.1 or something. So it can go up and down with this. And it doesn't really matter what actual sample rate you send out to the TV, because you'll always have to handle 2 samples per scan line sometimes. And this cubic stuff isn't very expensive anyways. Like you can see on the camera, the resampling, I think it's like the blue part at the very edge here. So it's really not very very intensive at all on the CPU.
Hey, I was looking at the forum post you put up there. What logic analyzer are you using?
Hot trash.
Oh, wow. Okay. Yeah. Just inexpensive stuff.
Analyzer. 24 megahertz, 8 channels. Believe it or not, getting full speed to work on Ubuntu is like awful, because the idiots broke it in their repo and refused to fix it or something. Oh, no. You have to install the like Debian version from like a file, but then you realize that technically it's not full speed that's broken, it's libsigrok that's broken. So then you realize that
yep, I remember that.
This kind of thing needs a firmware package. So then you install the firmware package. It doesn't tell you that you need the firmware package. You just kind of have to guess that. Right. It just says error opening device. So you have to install the firmware package for this. But by some sort of divine comedy, it reinstalls the stock repo version of libsigrok that doesn't work properly.
Oh, geez.
And because some deeply intelligent person at Ubuntu decided to enable link time optimization for all packages by
Oh, geez.
default. We should think it's a good idea, but GCC is not a good idea. So it ends up breaking the package somehow. Like the compiler bugs it. And for some reason they didn't fix it. Maybe they fixed it in 23.10, but if I do the upgrade, who knows? Or maybe I'll have to install it again.
Maybe it's
on the
definitely
file. I don't know. I think like a critical bug fix where the package doesn't work at all should be pushed at all costs. But I don't know. Like the package is already broke. You literally cannot use the lipstick rock that Ubuntu gives you. It there's like a drop down and pulls you. You can select the device. It's empty because it's broken. It doesn't know any devices because it's broken. It's just why. Anyways, it works now. Except it doesn't work because pulse view is ass. And the signal analyzer sort of part where you can like tell it how to decode the signal is written in Python, like the format decoders are written in Python, so they like lag your whole computer when you enable them. Great job, guys. And also whoever wrote the SPDIF one needs to have like pain happen to them because it's like sometimes it crashes when the signal that isn't like perfectly aligned to the start of the capture. Like when you start at midway through the capture, I have like a weird glitch in there. It just says, "Oops, I'm crashed. I'm gonna stop decoding the rest of the capture now." And you can't really tell it to start at a particular. It will always start trying to decode at the beginning of the capture. So if it takes a while for the signal to start, it will think that the bitrate is 0, and then it will do a divide by 0, and then it will crash. And it will just like put this little error box into the thing. And if that doesn't happen, it will again it will very slowly decode it and lag the whole computer while it's doing it because. Can we please have software that works? No, we can't. It's forbidden. Someone has decided that all the software must be slow. Because today we don't put in intellectual effort, we just copy, we paste. And then we sort of make it work. Maybe it's like a proof of concept, don't look at it. And then no one ever does the proper version, and it just sort of gets into that point where it kind of works good enough, but no one wants to fix it. But it's also not good and not actually good. It's actually, and that's a lot of software. It gets into that space, especially if it's like a free software sort of project where there's a paid version that does work properly. But like you can kind of use the free version, so it's like, oh, no one wants to fix it.
Well, Ada, let me interrupt. I have to leave. Good seeing you all and hearing you all today. And I'll look forward to next time. Next year, I guess, huh? And Chip will be releasing, I'm hoping to release your driver version next week.
Okay,
So,
good.
Until I get back to my machine, which will be late Friday, I'm not working on it.
Right on. Okay. Well, have
Okay.
a good trip.
Thank you.
Have
We'll
fun,
see you.
everyone. Bye.
Ooh. Should I stop recording now? We're still recording. Let's see here. There we go.